Hello there, and welcome to Science for Sleep, the quiet corner of the internet where science slows down, curiosity softens around the edges, and ideas stretch out just enough to help you unwind. Tonight, we're settling into one of the strangest puzzles in physics, something so familiar that you feel it every day, yet so puzzling that entire fields of research have grown around it. It's the force that keeps your feet on the floor, pulls the tides across the shorelines, and holds entire planets in place. And oddly enough, it's also the weakest force in the universe by far. So quiet, so gentle, so subtle, that a small fridge magnet in your kitchen can overpower the gravitational pull of the entire Earth. That contrast alone is enough to make anyone blink a little slower and wonder what's going on behind the scenes. We're talking about gravity tonight, and not just the ordinary pull you've known your whole life. We're looking at a question that physicists whisper about in lecture halls and debate over late-night emails. Why is gravity so weak compared to the other forces of nature? Why can it shape galaxies yet lose a strength contest to a tiny magnet? And why do some scientists think the answer might involve dimensions we can't see, drifting around and behind the familiar world we move through? There's a strange and compelling idea called the Gravibrane theory, suggesting that gravity may not be confined to our universe the way other forces are. Instead, it might wander or leak or stretch into hidden dimensions, quietly distributing its influence somewhere beyond our direct view. Before we go any further though, I'd love to know where you're listening from tonight. Maybe you're curled up on a couch, winding down after a long day. Maybe you're watching from a city with bright lights and late evenings, or a small quiet town where the night settles early. And as you listen, what time is it for you right now? The topic may be gravity, but it's always grounding to remember that you and I are having this moment inside a very real slice of time and place. All of us scattered around the world, each hearing these words in our own way, in our own space, with our own version of what nighttime feels like. If you find this kind of slow exploration soothing, if these gentle wanderings through science help you ease into rest or give you a peaceful pause before sleep, I'd be grateful if you'd tap the like button or subscribe. It helps this cozy pocket of calm find more people who need it. And with that, let's take our first quiet step into this strange question that has puzzled scientists for generations. Gravity doesn't usually feel weak. When you trip or drop your phone or try to lift something heavier than you expected, it feels pretty persuasive. But in the grand scheme of physics, gravity is nearly insignificant. Compare it to the electromagnetic force, the strong nuclear force, or the weak nuclear force. And gravity sits at the bottom of the list by an enormous margin. This isn't a small difference. It's not even a difference of thousands or millions. Gravity is weaker by a staggering number. A simple example illustrates it clearly. Take that fridge magnet again. When it clings to the metal surface, it isn't doing much in your everyday experience. But from the perspective of the universe, that tiny magnet is performing an astonishing feat. It's overcoming the gravitational pull of an entire planet. Something doesn't add up. Why should one of the most essential shaping forces of the cosmos be so faint when measured next to the others? Physicists sometimes call this the hierarchy problem. It's the imbalance in strength between the forces. Not a small imbalance, but one so enormous that it begs for an explanation. If all the forces comes from the same fundamental reality, if they emerged from the same conditions, why should one of them barely whisper while the others shout? The universe isn't usually that uneven without a reason, and for more than a century researchers have tried to make sense of this peculiar weakness. Some have suggested that maybe gravity isn't weak at all. Maybe it only looks weak because we're not seeing the full picture. Maybe the force we feel is only a small part of something bigger, something that extends into places we can't directly observe. Imagine for a moment that the world around you is like the surface of a sheet. You can move left, right, forward, and backward, but only along the sheet. Now imagine there's a space above and below the sheet that you can't reach, but something else can. Something like gravity. In this idea, the electromagnetic force and the nuclear forces stay trapped on the sheet, strong and concentrated because they can only operate within that thin surface. But gravity, instead of being stuck, might be able to drift off the sheet, spreading its influence into additional dimensions. If that were true, the gravity we feel would be only the portion that stays behind, a kind of leftover that remains on our sheet, while the rest disperses into a wider realm. That would make gravity appear weak even if, in the full dimensional space, it's actually strong. This is one of the central ideas behind Gravibrane theory. The word brain comes from membrane, a structure in theoretical physics that represents a kind of surface embedded in higher dimensional space. According to this view, our entire universe might be a brain floating in a higher dimensional environment. We can move within our familiar 3 dimensions, but gravity might seep into others. You could think of it like sound travelling through different rooms. If a speaker is playing music in one room, you might hear it clearly when you're inside that room, but once you step into a hallway or into another room further away, the sound becomes faint, even though the speaker itself hasn't changed. Gravity might be doing something similar, except the rooms aren't places you can walk to. They're additional dimensions beyond our senses. People often imagine extra dimensions as some kind of fantasy, but in physics they're not introduced for decoration. They're introduced because the equations point toward them, because certain problems suddenly become solvable when you allow for more dimensions than the ones we see. And gravity's weakness is one of the clearest hints that the universe might be more layered than it appears. But before jumping deeper into that idea, it helps to step back and think about what we expect from gravity. Most of us grow up thinking about it as a force that pulls things downward. Objects fall, planets orbit, moons drift around their parent worlds. But gravity isn't just a pull. According to general relativity, gravity is the curvature of space-time itself. Massive objects bend the geometry around them, and smaller objects move along those curves. It's a bit like placing a heavy ball on a stretched sheet. The ball creates a dip, and smaller objects naturally roll toward it. The more massive the object, the deeper the dip. This bending of space and time is gravity. And in this view, gravity isn't weak because it's failing to pull hard enough. It's weak because space-time itself resists being curved, or because the curvature spreads out more than we realise. If space-time had additional directions to bend into, that curvature might not stay concentrated in our familiar dimensions. Instead, the shape created by mass could extend into hidden spaces, diluting the effect we observe. This wouldn't be gravity acting poorly, it would be gravity acting expansively. This idea changes how we think of ourselves in the universe. For centuries, we assumed that what we see is all there is, that the dimensions accessible to our senses are the full story. But physics has gradually nudged us toward a different picture. Light reveals only a small fraction of what exists. The visible portion of matter is tiny compared to what lies hidden. Dark matter and dark energy fill most of the cosmos, and now, there's the possibility that even the structure of reality itself includes layers we haven't yet felt. Gravity may be our first clue, the faint footprint of something moving beyond the walls of our observable world. But even with this possibility in mind, the question remains, why would the universe be built this way? Why would some forces stay confined to a brain while gravity is free to roam? What makes gravity different enough to take on this peculiar role? Scientists who study brain-world theories have proposed that the fundamental particles responsible for the electromagnetic and nuclear forces are anchored to the brain because of how they interact with fields that are intrinsically part of it. Gravity, however, emerges from the curvature of space itself, and if the full space includes more dimensions, then gravity naturally belongs to the whole structure, not just the surface layer. You can picture it like paint soaked into a piece of fabric. Most substances would remain on the surface, unable to seep through. but something thinner and more fluid might travel through the threads and reach other layers. Gravity could be that thin, penetrating influence, reaching between the dimensional layers of reality. As you let this idea settle, notice how strange and yet grounded it feels. Gravity is familiar. It's the force we experience constantly without trying, and yet beneath that familiarity lies a puzzle that has pushed physicists towards some of the most imaginative theories ever proposed. That blend of everyday experience and deep mystery makes gravity a perfect guide for nights like this. Not harsh or demanding, just curious and steady. These questions don't need quick answers. They unfold slowly, like a long walk through a quiet place where the landscape shifts gently and reveals something new each time you look around. We're only taking the first steps here, easing into the puzzle, letting the pieces come into focus. There's no rush, only a calm exploration of a universe that always has another layer waiting just behind the one we think we know. And as the thought of gravity's weakness begins to settle into your mind, you might feel a kind of quiet fascination at how something so constant can be so incomplete in our understanding. That gentle uncertainty is part of the journey. It opens the door to all the questions that follow, each one carrying us a little deeper into the idea that maybe the universe has more dimensions than the ones we see, and that maybe gravity has been wandering among them all along, leaving us to feel only the faintest portion of its true presence, while the rest stretches out into spaces where our senses cannot follow. Gravity is easy to overlook because it never stops working. It follows you from the moment you wake up until you finally settle into sleep. You never have to switch it on, recharge it, or wonder if it might suddenly lose interest and drift away. It is always there beneath your feet, leaning gently on every part of your body, shaping how you move, how you rest, how you exist in space. And even though it's so dependable, there's something almost quiet about the way it acts. It doesn't buzz or flash or spark. It doesn't launch particles across the room or twist atoms together in a burst of energy. It simply pulls steadily and without fuss, holding things in place while the rest of the universe races around with far more intensity. It's strange to think that this constant presence, this soft background pull, is one of the weakest influences in all of nature. The solidness of the ground beneath you, the weight of the objects you lift, and the entire architecture of the solar system feel like evidence of a force that should be immensely powerful. Yet when compared with the other forces that govern the universe, gravity almost disappears. The electromagnetic force can lift a paperclip with a small magnet. The strong nuclear force binds protons together inside atoms with unimaginable strength. The weak nuclear force shapes the process of radioactive decay. All of these display their effects with energy and precision that gravity simply cannot match on small scales. And yet, despite all of that, gravity is the one you interact with most directly. The others rarely make themselves obvious unless you build equipment designed to reveal them. Gravity is the force that gives you a sense of direction, that tells you what is up and what is down. It's the reason you feel the pressure of your body against a chair or a bed. If that pressure suddenly vanished, even for a moment, the world would feel alien. It's comforting in a way that something so subtle can be so dependable. The quiet strength beneath your feet is something you've felt since the day you were born, long before you understood anything about how it works or where it came from. As you move through your day, you might not notice how gravity reshapes your perception of everything around you. The way you gauge distance is influenced by it. The effort you need to climb a staircase, the balance you keep while walking across a room, even the rhythm of your breathing shifts depending on how your body positions itself in relation to the Earth's pull. It's woven into every physical sensation so seamlessly that you rarely stop to think about it. That seamlessness is partly what makes the weakness of gravity so surprising to scientists. If a force so gentle can influence so much, what must the stronger forces be doing behind the scenes? When physicists began to measure the strength of each fundamental force, They didn't find a modest difference between gravity and the rest. They found a gap so enormous that it forced them to reconsider their assumptions. It wasn't the kind of difference you could explain by saying one force is slightly more efficient or one acts over a shorter range. They found a difference so staggering that they had to question why gravity operates so differently from all the others. The contrast created a puzzle that continues to guide modern physics. If gravity shapes the structure of galaxies, why is it so feeble when measured at the scale of atoms? Why does the universe allow it to be both essential and nearly absent depending on where you look? One way to get a sense of this imbalance is to think about how particles interact. When two charged particles come close to each other, the electromagnetic force between them is so strong that it dwarfs every other influence except, under extreme circumstances, the strong nuclear force. Gravity between those same particles is so tiny that for most practical purposes it might as well be zero. If you calculate the gravitational pull between two electrons, you'll find that it is roughly 40 orders of magnitude weaker than the electromagnetic repulsion between them. That number is beyond everyday experience. It's not the kind of difference you can imagine with a simple comparison. It's more like trying to picture the difference between a grain of sand and an entire galaxy. Those enormous numbers force physicists to look for a deeper explanation. Forces don't usually behave so inconsistently unless something else is shaping the outcome. For many years, gravity's weakness was simply accepted as one of the mysteries of the universe. Scientists could describe what gravity does, how it behaves, and how it influences the motion of objects, but they couldn't explain why it had the strength it does. Newton described gravity as a force that acts at a distance. Einstein later reinterpreted it as the curvature of space-time itself. Both frameworks explained what gravity does remarkably well, and both have been tested countless times with consistent results. But neither explanation answered the question of why gravity seemed to hide its full strength, or why the other forces seemed to dominate so easily. As technology improved, physicists began searching for ways to unify the fundamental forces. They hoped to create a framework in which everything could be described in the same language, a set of equations that would show how the forces relate to one another. Models describing the electromagnetic force, the weak force, and the strong force eventually merged into what is known as the Standard Model of particle physics. This model is incredibly successful at predicting and explaining countless phenomena, but gravity resisted being absorbed into this structure. It sat outside the equations, behaving differently, refusing to match the patterns of the other forces. Its weakness made it difficult to analyze at the quantum scale, where the other forces operate most intensely, and so researchers began to explore ideas that might explain gravity's unusual behavior in a broader context. If a force doesn't match the others, maybe it's not meant to. Maybe it emerges from a different underlying structure. Maybe the universe has layers or features that aren't obvious from our viewpoint, and gravity interacts with those hidden layers in ways the other forces do not. This line of thinking gave birth to theories that involve extra dimensions, branes, and higher dimensional spaces. These ideas weren't invented on a whim. They were created because gravity's weakness demanded an explanation that couldn't be found in the familiar three-dimensional world. While these theories can be mathematically complex, the underlying concept is surprisingly intuitive. If gravity spreads itself through additional dimensions, then the portion we feel here is only a fraction of the full force. Meanwhile, the nuclear forces and the electromagnetic force remain confined to our familiar dimensions, meaning they don't thin out in the same way. In this picture, gravity isn't inherently weak, it's diluted. It's present everywhere, but it is also distributed across more space than we can perceive. This shift in perspective changes how you think about the strength beneath your feet. Instead of imagining gravity as a small force that struggles to keep up with the others, you start to see it as a widespread influence that simply has a broader job. The other forces act within the tight, compact structure of our three-dimensional space. Gravity acts throughout a much larger framework. It's doing more, reaching further, and covering territory the other forces can't access. When you think about it this way, gravity's quiet nature becomes more understandable. It's not weak because it's ineffective. It's weak here because it might be strong somewhere else. The idea that forces can behave differently depending on the dimensional structure of the universe helps make sense of some puzzling observations. For example, the way gravity behaves at very large scales fits with the idea that it stretches outward into space with incredible persistence. It keeps entire galaxies bound together, even when those galaxies are separated by unimaginable distances. But on the scale of atoms, where the other forces dominate, gravity becomes almost irrelevant. That behavior can be interpreted as gravity working within a much larger arena than the others. The other forces are like specialized tools, strong and focused within particular environments. Gravity is like a background influence spread thinly across a much broader landscape. Even within our own bodies, gravity's influence is both subtle and central. The way your muscles develop, the way your bones maintain their density, and even the way your heart pumps blood is shaped by the steady downward pull. Without gravity, the body begins to adapt in ways that feel unnatural. Muscles weaken, bones lose minerals, balance becomes unpredictable. Astronauts experience these changes quickly because there's no gravitational anchor to give their bodies the reference points they're accustomed to. The strength beneath your feet is not just a physical force, it's also a biological environment. It shapes the design of every living thing on Earth. That close relationship makes gravity feel more familiar than the other forces, even though it is far more mysterious. You never feel the strong nuclear force directly. It binds atoms together, but it never touches your senses. You don't feel the weak nuclear force or the electromagnetic forces inside your body. Gravity is the only one that interacts with your entire being in a constant and physical way. It doesn't need special equipment or unusual circumstances to reveal itself. It speaks to you through pressure, through balance, through motion. That familiarity gives it a kind of quiet authority, even though in the grand hierarchy of forces it sits at the bottom. And yet, despite how gentle it feels, gravity can become overwhelming under the right circumstances. On planets larger than Earth, gravity becomes strong enough to crush bone structure, making the idea of human exploration there a severe challenge. Near massive stars or black holes, gravity becomes intense enough to distort time itself. These extreme environments are reminders that gravity's quietness is only part of its personality. It can become powerful when mass accumulates. It can bend light, slow clocks, and reshape space. Its behavior is subtle but far-reaching, soft but capable of dramatic effects when the circumstances align. The ground beneath your feet is the calm version of gravity, the form that supports life and gives the planet its stability. But the universe contains places where gravity's full influence becomes much clearer. Exploring why gravity ranges from gentle to overwhelming is part of what motivates physicists to understand its true nature. If gravity is capable of expressing itself in so many different ways, then perhaps its weakness here is not the defining trait. It may be a hint about how it interacts with the deeper structure of reality. Thinking about these possibilities can make the everyday experience of gravity feel different. Instead of being just a simple downward pull, it becomes a sign of something much larger and more intricate. The sensation of your weight against the floor becomes a subtle reminder that the force holding you there may be connected to an architecture of dimensions that lie beyond your perception. It's a small, steady expression of a much larger story. That thought offers a kind of gentle curiosity. It lets you picture gravity not as a limited force, but as one with depth that we haven't fully accessed yet. The quiet strength beneath your feet might be coming from a wider system, one that we are only beginning to understand. Gravity is often described as the force that holds the universe together, but when you look at the numbers behind it, the phrase feels almost ironic. Something so light, so faint, so easily overshadowed by stronger interactions is responsible for the structure of galaxies, the orbits of planets, and the slow choreography of cosmic evolution. It's as if the universe entrusted its grand architecture to something that, on a local scale, barely registers. When scientists compare the strength of gravity to the other forces, they often end up shaking their heads at the contrast. Even though gravity shapes the largest structures known, the force itself behaves like a feather resting on a scale compared to the hammer strikes of the strong nuclear force, or the precise push and pull of electromagnetism. Thinking about that contrast can be a bit disorienting at first. We tend to associate big effects with big causes. If something shapes the cosmos, we expect it to be powerful in a way that we can directly feel. Yet here we are, living on the surface of a planet held steady by a force so faint that it's practically invisible when acting between small objects. That mismatch is part of what makes this question so compelling. Gravity feels strong because we experience it constantly, but its actual strength, in the technical sense, is small enough to confuse even experienced physicists. A useful way to understand this is to imagine two objects floating close together in space. If they are neutral objects with no electric charge, gravity is the only force acting between them. It gently draws them together, slow and quiet, almost like the gradual drift of two pieces of dust settling on a table. Now imagine another pair of particles, these with opposite electric charges. The electromagnetic force between them is so much stronger that the comparison barely makes sense numerically. The electromagnetic force is so overwhelmingly powerful that it binds atoms, drives chemical reactions, shapes materials, and makes almost every interaction you encounter daily possible. Yet gravity, which is unimaginably weaker, is the force we feel most consistently. This leads to an odd sense of contradiction. How can a universe built on fundamental interactions allow one of them to be so diminutive? And why does this tiny force end up determining the large-scale fate of everything from moons to galaxies? The answer comes from the way each force behaves across different distances. The nuclear forces, for example, only act over extremely short ranges. They do their work inside the nucleus of an atom and drop to zero just a short distance away. Electromagnetism is stronger and extends further, but it's also balanced in many situations by the fact that positive and negative charges often cancel out. In large structures, atoms tend to form neutral configurations, meaning that their electromagnetic forces largely balance to zero. That leaves gravity as the only force that accumulates rather than cancels. Mass adds to mass. Every bit of matter contributes to the total gravitational pull. The more mass you gather, the stronger the effect becomes. This cumulative nature explains how a force that feels so subtle on small scales can dominate on large ones. A single object has weak gravity, a planet has stronger gravity, a star has even more. Galaxies gather trillions of stars and clusters of galaxies gather thousands of galaxies. The result is a gradual amplification that transforms a tiny influence into the dominant force shaping the structure of the cosmos. The universe becomes something like an enormous web woven from countless faint threads, each contributing a tiny portion of pull. None of those threads is strong by itself, but together they create the framework that holds everything in place. Physicists often point to this cumulative behavior when explaining gravity's role. But even with that understanding, the question remains: why does each individual thread have so little strength? Why is the basic interaction underlying this grand cosmic structure so minimal compared to its siblings in the family of forces? Many scientific ideas attempt to give gravity a deeper context, suggesting that what we observe might be only part of a wider picture. One idea that helps make sense of gravity's faint nature involves the energy scale at which each force becomes significant. The strong nuclear force and the weak force operate at energy scales associated with subatomic particles. Electromagnetism spans a wider range because it acts on charged particles and structures at everyday scales. Gravity, however, becomes dominant only when huge amounts of mass accumulate. This difference in energy scales is part of what scientists call the hierarchy problem. why is gravity's characteristic energy scale so much lower than that of the other forces? The numbers differ so drastically that researchers are convinced something deeper must be influencing the relationship. As theories evolved, some physicists began exploring the idea that gravity might not be confined to the same dimensional space that the other forces occupy. If forces such as electromagnetism are restricted to our familiar 3 dimensions, but gravity can move through additional dimensions, it would naturally appear weaker here because its influence is spread across a larger volume. It's similar to shining a flashlight directly on a wall versus shining it into an open space. The same light source produces a bright spot on a surface, but becomes diffuse when it spreads out into a larger area. When applied to gravity, this idea suggests that the force we experience is only a fraction of the total influence. Most of it could be extending into dimensions beyond our perception. In that case, gravity is not so much weak as it is dispersed. We feel only the part that remains on our 3-dimensional world, much like hearing only the echoes of a sound that originated in a much larger space. This picture can make the universe feel less puzzling and more layered. Instead of living in a simple 3-dimensional container, we might be part of a deeper structure that uses additional dimensions to explain the patterns we see. The quiet strength of gravity becomes a clue rather than an anomaly. It becomes a signpost pointing toward a more complex architecture underlying the familiar world. Even if you set aside the possibility of extra dimensions, the behavior of gravity still raises interesting questions. The laws that describe it at large scales work extremely well, but as you move into very small distances where quantum mechanics dominates, the equations become less reliable. Attempts to merge gravity with quantum mechanics often run into mathematical difficulties. Some approaches suggest that gravity might not be a fundamental force at all, but could be something that emerges from more basic principles, similar to how temperature emerges from the motion of particles rather than existing as an independent phenomenon. In this view, gravity might be the large-scale result of microscopic interactions that we have not yet identified. Instead of being a primary ingredient of the universe, it could be a secondary effect that arises when matter and energy organize themselves in certain ways. That possibility changes how you interpret gravity's faintness. If it emerges from deeper processes, it might naturally behave differently from the other forces. Its weakness might be a sign that it isn't fundamental but derivative, showing up only when systems become large enough for certain patterns to appear. Thinking about gravity this way can make the universe seem both more intricate and more comprehensible. Instead of treating gravity as an outlier that refuses to fit into existing frameworks, you begin to see it as a phenomenon shaped by deeper laws. Its faintness becomes an indicator that it interacts with reality differently. The universe might be held together by something that behaves like a feather, because the underlying mechanism doesn't rely on brute strength. It relies on accumulation, geometry, and the behavior of space itself. When astronomers observe the large-scale structure of the universe, they see patterns shaped primarily by gravity. Galaxies gather into clusters, clusters form filaments, and those filaments weave into a vast network. That structure resembles a kind of cosmic scaffolding. Even though gravity is faint, its ability to accumulate means that over billions of years, it gradually organizes matter into these large formations. It doesn't push or pull with sudden burst of force. It nudges everything slowly, allowing patterns to develop over immense spans of time. The comparison to a feather becomes fitting not because gravity is soft, but because the effect is gradual. The universe doesn't need a hammer to shape itself. It uses the quiet consistency of gravity to create the structures we observe today. This perspective also explains why the universe looks the way it does at different times. Shortly after the Big Bang, matter was distributed relatively evenly. As gravity began to act, small variations in density became seeds for future structures. Regions slightly denser than average attracted more matter. Over time, those regions grew into the galaxies and clusters that now fill the cosmos. That entire process was driven by the faint pull of gravity accumulating slowly. It wasn't sudden or explosive, it was steady and persistent, working over billions of years. The softness of gravity becomes part of its character rather than a flaw. It's a force that shapes the universe quietly, without the violent interactions of nuclear forces or the precision of electromagnetism. It's patient in a way that the others are not. Its weakness allows the universe to evolve gradually, rather than collapsing quickly into dense structures or dispersing in chaotic ways. The balance created by gravity's low strength is part of what makes long-term stability possible. If gravity were stronger, the universe would have formed differently. Stars might have collapsed more quickly. Planetary systems might be less stable. Galaxies might have taken on entirely different shapes. If it were weaker, matter might not gather into large structures at all. The conditions needed for stars, planets, and eventually life might never arise. The faintness of gravity is not accidental. It plays a role in shaping everything from the cosmic web to the conditions on individual planets. That thought adds another dimension to the discussion. Instead of asking why gravity is weak compared to the other forces, you begin to wonder why the universe needed it to be this way. Its weakness is part of the environment that allows complexity to emerge. Stronger forces dominate at small scales. Gravity takes over at large ones. Together they create a balance that produces stable atoms, stars and galaxies. The feather-like nature of gravity becomes a feature that enables the universe to function as it does. As you let that idea settle, the sense of contradiction fades. The universe isn't held together by something weak, it's held together by something steady. The faintness of gravity doesn't reduce its significance, it makes its role possible. And while physicists continue to search for the deeper reasons behind its low strength, the way gravity behaves has already shaped everything we see. This understanding lays the foundation for the ideas that follow, including the possibility that gravity is part of a larger structure linking multiple dimensions or branes. If gravity truly extends beyond our familiar space, then the feather-like pull we feel might be just one small piece of a wider influence. When people first learn that the universe runs on just a handful of fundamental forces, the idea seems simple enough. 4 basic interactions shaping everything from atoms to galaxies: the electromagnetic force, the strong nuclear force, the weak nuclear force, and gravity. But when you look closely at how these forces behave, the simplicity dissolves almost immediately. Instead of a neat set of equal partners sharing responsibility, the forces turn out to be dramatically unbalanced. They sit at very different strength levels, separated by gaps so immense that the comparisons feel almost unreasonable. The universe is built from interactions that differ not by small percentages, but by differences measured in dozens of orders of magnitude. This imbalance isn't something anyone would naturally expect. When scientists try to explain the underlying rules of reality, they often look for patterns, symmetries, or relationships that tie everything together. But the raw numbers behind the forces defy that expectation. The strong nuclear force is unbelievably powerful, but acts only inside the tiny space of an atomic nucleus. The weak nuclear force is much lighter in strength and responsible for certain types of radioactive decay. The electromagnetic force acts over a wide range and is responsible for almost everything you can touch, see, or feel in your daily life. And then there's gravity, sitting far below the others like it wandered into the wrong category by mistake. To get a sense of how extreme this imbalance is, imagine comparing the strength of electromagnetism to gravity between 2 protons. If the electromagnetic repulsion between them were equivalent to the weight of a mountain, the gravitational attraction between them would be like the weight of a single grain of sand. That difference is not a minor gap. It's a gulf that challenges every assumption physicists have about unity among the forces. If the fundamental structure of the universe emerged from the same early conditions, why does one interaction explode with power while another barely registers? There must be something beneath the surface shaping these differences. The strong nuclear force, for example. is the reason why the protons in an atomic nucleus can stay together. Electromagnetism pushes them apart because, like charges, repel. But the strong force binds them with such overwhelming strength that the repulsion becomes irrelevant within the confines of the nucleus. That force feels almost violent when described mathematically. If the strong force extended even a little beyond nuclei, matter as we know it would behave in completely different ways. The boundaries between atoms would be impossible to maintain. Everything would fuse, collapse, or shred apart long before the universe had a chance to form stars or planets. The weak nuclear force, despite its name, is still astronomically stronger than gravity. It operates in processes like beta decay and plays a crucial role in how stars produce energy. Though its effects are subtle in daily life, the weak force is essential to the chemical diversity of the universe. Without it, stars would not fuse elements the way they do, and many of the atoms you're familiar with simply wouldn't exist. Even here, at this weak level, the difference compared to gravity remains enormous. Electromagnetism acts across much larger distances and displays a level of strength that allows it to dominate most familiar interactions. Every time you pick something up, turn on a light, swipe a screen, or feel the texture of an object, the electromagnetic force is responsible. It governs the structure of atoms, molecules, and materials. It shapes chemical reactions and organizes the matter you interact with constantly. And unlike the nuclear forces, which operate only within tiny regions, electromagnetism reaches across large spans of space. That range, along with its strength, explains why it's so influential in everyday physics. Gravity, however, does not appear to match any of these behaviors. It's weak, it's cumulative, and it acts across vast distances. It doesn't confine itself to regions like the nuclear forces. It doesn't cancel out the way electromagnetism often does when charges balance. It grows steadily as mass accumulates, but its effect on small scales is so faint that even simple laboratory experiments struggle to isolate it from background noise. This mismatch between gravity and the others forces the question of how all four interactions came to exist with such different properties. Scientists refer to this puzzle as the hierarchy problem, not because it's a problem in the everyday sense, but because it highlights a hierarchy of force strength that seems unnatural. Physics often seeks explanations that reduce the number of arbitrary differences in nature. When something stands out as dramatically uneven, researchers assume there must be a deeper mechanism hiding behind the surface. The strengths of the forces shouldn't need to be wildly different unless something in the structure of the universe requires it. The spacing between these forces becomes even more puzzling when you consider attempts to unify them. Some theories propose that at very high energies, such as those present shortly after the Big Bang, all forces were once the same. If the universe began with a single unified interaction, then the extreme differences we observe today must have developed as the universe cooled and expanded. The act of splitting one unified force into several distinct ones would have required symmetry-breaking processes, similar to how water can turn into ice with a crystalline structure completely different from the liquid form. In this analogy, the forces would be like different patterns emerging from a single material under different conditions. But even with that picture in mind, the sheer scale of the differences remains difficult to explain. The strong nuclear force sits at the top of the hierarchy, millions of times more powerful than the weak force, and the weak force is still many orders of magnitude stronger than gravity. The structure looks almost like a ladder, with rungs spaced unevenly, as though someone stretched the distance between two of them far beyond the others. That stretched region is where gravity sits, far below the rest, quietly pulling, but never matching the strength of its companions. This imbalance is part of what motivated physicists to explore theories involving extra dimensions or branes. If gravity can travel beyond the space in which the other forces operate, its apparent weakness becomes a natural outcome. The strong, weak, and electromagnetic forces might be confined to a lower dimensional surface, a kind of sheet embedded in a higher dimensional space. Gravity, unlike the others, could move through the surrounding space as well. That would dilute its strength in the familiar dimensions, much like a drop of ink dispersing through a large volume of water. You see only the small portion that remains in your region, but the rest spreads outward. The idea is not simply a creative metaphor. It comes from mathematical models that attempt to unify gravity with quantum mechanics. When scientists tried to force gravity into the same framework that describes the other forces, they encountered inconsistencies that made the equations collapse at extremely small scales. That failure led to the suspicion that gravity might not originate from the same kind of particle interactions as the others. Instead, it might emerge from the shape or curvature of space itself, rather than from an exchange of force-carrying particles like photons or gluons. If gravity is tied closely to geometry, then introducing additional dimensions naturally changes its behavior. The more directions space can bend, the more diluted the curvature becomes in any one part of it. That perspective makes gravity look weak not because its fundamental influence is small, but because the environment in which it acts is larger than we can perceive directly. Meanwhile, the other forces remain tightly confined to our familiar dimensions, retaining their full strength. Even if you set aside extra dimensions and brains, the imbalance among the forces still demands an explanation. The strengths of the strong, weak, and electromagnetic interactions can be traced through models that relate their energy scales. Gravity stands apart because its characteristic scale, known as the Planck scale, is vastly higher. If you calculate the energy required to probe gravity at the quantum level, the required numbers exceed the energies reached in particle accelerators by an unimaginable factor. This gap between the Planck scale and the electroweak scale, where the weak force becomes relevant, is part of the same imbalance problem. Researchers have attempted to narrow this gap by proposing mechanisms such as supersymmetry, which would balance masses and forces more evenly at high energies. These attempts aim to bring gravity and the other forces closer together conceptually, but even supersymmetry, elegant as it is, does not fully resolve the magnitude of the difference. The imbalance persists unless something in the structure of space spreads gravity thinly. The strange part about this situation is that the imbalance is both a problem and a necessity. If the strong force were even slightly weaker, atomic nuclei wouldn't hold together. If the electromagnetic force were stronger or weaker by even modest factors, atoms and molecules would not form in stable ways. If the weak force behaved differently, stars would not carry out the fusion processes that create elements heavier than hydrogen. And if gravity were dramatically stronger, many regions of the universe would collapse quickly. If it were dramatically weaker, matter wouldn't gather into stars or planets at all. This suggests that the strengths of the forces are not random. They sit at very specific values that allow complex physical structures to emerge. The imbalance isn't just a curiosity. It's a requirement for the universe to function the way it does. But that still leaves the question unanswered. Why does nature choose these values in particular? And why does gravity sit so far below the others in strength? Some theories propose that the force strengths might not be fixed universally. They could vary across a larger multiverse, and we happen to live in one region where their values allow stable structures. This idea, though speculative, arises naturally from certain interpretations of high-energy physics. If the universe is broader than what we observe, containing regions where physical constants differ, then the imbalance we see here might be one branch of many possibilities. But even this picture benefits from explanations involving extra dimensions, because the features of brain world theories fit neatly into scenarios where constants differ between regions. As physicists develop new models, the imbalance among the forces continues to serve as a guide. It indicates that gravity may be governed by rules that differ from those shaping the other interactions. Within that difference lies the potential explanation for why gravity seems to permeate through a larger region of space, or into more dimensions. It becomes a puzzle piece hinting that the architecture of the universe might involve layers or surfaces embedded within a higher dimensional environment. Thinking about this imbalance changes how you interpret the world around you. When you feel the pull of gravity holding you down, you're experiencing the faintest of the 4 fundamental interactions. Every physical sensation you associate with weight or steadiness comes from the least powerful force by an enormous margin. Meanwhile, the stronger forces work invisibly inside atoms and matter, organising the structure of everything you interact with, yet never making their presence directly felt. When physicists began measuring the world with greater precision, they expected the fundamental forces to reveal themselves as different versions of a similar theme. The early hope was that everything would eventually fit into one elegant framework, a set of rules simple enough to unify the behaviour of particles, fields, and forces. But the moment measurements became accurate enough to compare these interactions side by side, something felt off. Gravity behaved differently in a way that wasn't subtle. It was shy. Not timid in a figurative sense, but measurably quiet. Even in experiments designed to amplify its influence, gravity refused to reach the levels the other forces achieved with ease. This shyness wasn't immediately recognised for what it was. The earliest understanding of gravitational strength came from large, everyday phenomena. Apples falling, planets orbiting, tides shifting. To people observing only these familiar events, gravity didn't look weak at all. If anything, it seemed powerful. It could pull oceans across continents. It could hold the moon in its place. It could organise the motion of the planets with enough precision that astronomers could predict their positions centuries into the future. The first scientists who studied it wouldn't have described it as faint. They saw a force that ruled the motions of the heavens. It wasn't until experiments probed smaller scales that the picture changed. Early physicists had no concept of nuclear forces or quantum fields. They didn't know about the immense energies locked inside atoms. They had no way to compare gravity to the interactions that would eventually be discovered within the subatomic world. Only when new instruments allowed people to look inside matter did gravity begin to reveal its peculiar behaviour. It simply didn't compete with the other forces that appeared in this deeper arena. One of the earliest clues came from trying to understand why atoms didn't collapse. If electrons orbited nuclei the way planets orbit the Sun, electromagnetic attraction should pull them inward continuously, but atoms remained stable. That led to the development of quantum mechanics, which introduced new rules governing how particles behave. The electromagnetic force inside atoms turned out to be extraordinarily strong, enough to determine the structure of matter with precision. Gravity, by comparison, didn't even enter the equations. Its contribution was too small to affect atomic behaviour at all. When scientists realised this, they began to suspect something unusual. How could the force that shapes the solar system be irrelevant inside an atom? As technology advanced, the discovery of the strong and weak nuclear forces deepened the puzzle. The strong force was so powerful that it overcame the electromagnetic repulsion between protons in a nucleus. The weak force, though much lighter, still influenced particle interactions in ways gravity never did. Once the basic strengths of these forces were calculated, the numbers were so drastically different that researchers needed to re-evaluate what they thought they knew. The gap was revealed clearly when comparing the gravitational force between two protons to the electromagnetic force between them. The electromagnetic repulsion wasn't just stronger, it was stronger by a factor so large that scientists struggled to find meaningful analogies. That stark contrast made gravity look like it was barely participating in the small-scale world. If the forces were siblings, gravity seemed like the one who avoided attention completely. This was the moment when gravity's shyness became undeniable. The universe had 4 fundamental interactions, but gravity refused to act like the others. It didn't respond strongly at the scales where the others dominated. It didn't provide noticeable competition inside atoms or molecules. It stayed in the background, doing almost nothing in situations where the others performed dramatic work. Physicists didn't immediately think gravity was leaking into other dimensions. They just knew something was wrong with the usual expectations. Measuring gravity directly in small systems turned out to be one of the most difficult tasks in physics. The equipment had to be extraordinarily sensitive. Experimental setups had to be isolated from vibrations, temperature changes, and even the slightest movement in the environment. The earliest experiments trying to detect gravitational attraction between small objects often failed, because the effect was too weak to distinguish from background noise. Even today, measuring gravity between laboratory-scale masses requires elaborate setups just to get a tiny, barely perceptible signal. This difficulty wasn't just an inconvenience, it was a sign. The other forces produced effects so large that experiments could easily detect them. Gravity required a careful environment and patience, as if it preferred to remain unnoticed unless coaxed into revealing itself. One famous early experiment that helped quantify gravity's behaviour was the Cavendish experiment, which measured the gravitational attraction between lead spheres using a torsion balance. The equipment had to detect an incredibly small twist in a wire caused by the faint gravitational pull between the masses. The measurement was so delicate that even the subtle movement of air or the shifting of the building's foundation could disrupt it. Cavendish eventually succeeded, but the difficulty of the measurement highlighted gravity's near invisibility on small scales. This early experiment set the stage for everything that followed. As better tools emerged, physicists pushed the limits of precision. They measured the strengths of the forces with increasing accuracy, always finding gravity far behind. They also explored how the forces changed with distance and energy. That behavior painted gravity as something that simply didn't scale the way the others did. The strong force dropped to zero at distances larger than an atomic nucleus. The electromagnetic force decreased gradually, but remained significant over large areas. The weak force acted only over small regions. Gravity persisted over infinite distances, but did so with barely any influence at all. These differences made researchers wonder whether gravity even belonged to the same category as the others. In particle physics, forces are described in terms of particles that carry interactions. Photons carry electromagnetism. Gluons carry the strong force. Bosons carry the weak force. Gravity's hypothetical particle, the graviton, remained, and still remains, undetected. Not because it doesn't exist, but because its interactions would be too weak to measure with current technology. That possibility made gravity seem distant, elusive, and shy in a way the others were not. The more physicists learned about the forces, the harder it became to justify gravity's low strength without additional assumptions. Why would nature allow such a dramatic imbalance? Why would the force responsible for the largest structures in the universe be so irrelevant at the smallest scales? These questions grew sharper as theories advanced. When the standard model of particle physics was completed, gravity remained left out. The equations describing the nuclear and electromagnetic forces were elegant and well tested. Gravity resisted that kind of treatment. Attempts to quantize it ran into contradictions. The numbers exploded into infinities that couldn't be handled. The usual tools worked for every other force but failed for gravity alone. This resistance suggested the possibility that gravity might not be a standard force at all. It might be an effect of something deeper, perhaps the shape of space, perhaps the structure of dimensions, perhaps some emergent behavior that only appears at large scales. These kinds of ideas didn't arise because physicists wanted something exotic. They arose because gravity's behavior refused to match expectations. In time, the idea that gravity might not be confined to the same dimensional space as the other forces began to gain attention. Physicists noticed that the equations describing gravity's behavior in general relativity allowed for straightforward extensions into higher dimensions. Meanwhile, the equations describing the nuclear and electromagnetic forces did not. There was no simple way for those forces to leak into extra dimensions, even if such dimensions existed. Gravity, however, seemed naturally suited to the possibility. This mathematical openness led to the development of theories that treated gravity as a geometric effect, not just a force. And once gravity was viewed this way, the possibility of extra dimensions became more than a curiosity. it became a potential explanation for gravity's faintness. If gravity was spreading through more space than we could perceive, then the portion we observed would naturally appear weaker. The idea did not come from imagination alone. It came from the numbers. The measurements revealed a pattern that suggested gravity was diluted by something the others were not interacting with. Physicists began testing the idea by looking for deviations from Newton's law of gravity at very small distances. If additional dimensions existed, gravity might behave differently when objects were extremely close together. The experiments improved over decades, reaching smaller and smaller scales. So far, the results have not definitively revealed extra dimensions, but they have also not ruled them out. The scales at which deviations might appear are incredibly small, requiring levels of precision at the limits of technology. Despite the uncertainty, the motivation remains strong. Gravity acting shyly is not something physicists ignore. It demands answers. The imbalance between the forces is too large to be brushed aside, and the consistent failure to unify gravity with the others only strengthens the suspicion that something fundamental is different about it. As more clues accumulated, the early observations that gravity was faint became part of a larger narrative. Each new experiment reinforced the basic fact. Gravity does not behave like the other forces. It reveals itself slowly, gently, and across long distances. It does not express itself loudly or aggressively. Even black holes, the most extreme gravitational environments known, demonstrate that gravity's influence depends on mass rather than on strength in the conventional sense. A black hole forms not because gravity suddenly becomes stronger, but because mass collapses into a region where curvature becomes intense. The shyness physicists first noticed wasn't a superficial trait. It was the first hint of a deeper structure. It suggested that gravity operates within an environment broader than the other forces, and that realization guided the shift from thinking about gravity as a simple weakening to thinking about it as a phenomenon distributed across more space than we realize. As these ideas settled into the scientific conversation, researchers found themselves gradually pulled toward the next steps. The tools they needed to understand gravity's faint nature required a new framework. They needed to think about space differently, to consider structures that extend beyond the familiar three dimensions, and to explore the possibility that the universe might be built on layers we cannot see but can infer from the way gravity behaves. When physicists finally reached the point where classical explanations could no longer account for gravity's strange behavior, they had to look beyond the familiar. The measurements were too consistent to ignore. Gravity acted as though something in its environment was larger, broader, or more spacious than the region the other forces inhabited. If a force spreads itself through a wider space, it naturally appears weaker in any one part of it. That simple idea opened the door to something that would have sounded speculative centuries earlier, but has become a serious part of modern physics: the possibility that the universe includes dimensions beyond the ones we can see. Before going further, it helps to acknowledge how deeply ingrained our perspective is. You grow up experiencing length, width, and height. Those three directions feel so complete that you rarely question whether there could be more. Everywhere you step, you move within those boundaries. Every object you handle has those same three extensions. They define the physical world in a way that feels absolute. That sense of completeness is an illusion, though, not because it's wrong for the world you interact with, but because the human perspective is shaped by what your senses can access. They evolved to detect the conditions most relevant to survival, not to reveal the underlying structure of the universe. The idea of hidden dimensions doesn't begin with imagination, it begins with mathematics. When physicists tried to unify the forces or solve inconsistencies in equations, they discovered that certain problems became simpler when additional dimensions were included. The equations describing gravity, electrons, quarks, and fields behaved differently when extended into a space with more directions available. In some cases, the math only worked if extra dimensions existed. In others, the math became elegant instead of tangled. The logic wasn't to add dimensions for dramatic effect, but to make the equations behave the way nature actually behaves. One of the earliest hints of this came from attempts to unify gravity and electromagnetism in the 1920s. The idea was simple on paper. If you added another spatial dimension, some of the equations naturally assumed a combined form that linked the two forces. The model didn't survive long because it couldn't explain the newly discovered nuclear forces, but the idea of using extra dimensions to unify physical laws remained compelling. As physics progressed, the concept of hidden dimensions reappeared repeatedly. Every time researchers approached the deepest puzzles, unifying forces, explaining particle masses, or resolving inconsistencies in quantum gravity, the possibility of extra dimensions surfaced again. It wasn't forced into the theories, it emerged from them. The mathematics gave the impression that 3 spatial dimensions might not be the whole story. The challenge was figuring out how extra dimensions could exist without being obvious. If there were directions we could move but didn't notice, why didn't objects drift off into those directions or appear differently? The answer came from imagining that extra dimensions might be shaped or curled in ways we can't access. Instead of being large and open like the familiar 3, they could be compact, folded, or constrained. Picture a thin garden hose. From far away, it appears one-dimensional. You move along its length but don't notice its circular cross-section. Only when you get very close do you see that it has another direction. In physics, something similar could be happening with extra dimensions that are compactified at scales far smaller than atoms. These compact dimensions became a cornerstone of theories like string theory, in which particles are viewed not as points, but as tiny vibrating strings. The vibrations produce the particles' properties, but the strings require additional dimensions to vibrate through. The equations describing them didn't work in 3 dimensions alone. They needed more. The exact number depends on the model, but common versions require 10 or 11 dimensions, with the extra ones compactified into shapes far too small for direct measurement. Even though this idea sounds complex, the underlying picture is straightforward. The universe could have more structure than we can detect. Our senses and instruments operate within the available 3 dimensions because those are the dimensions large enough to interact with. The smaller ones would hide not by being invisible, but by being too tightly folded to influence everyday physics directly. But gravity, unlike the other forces, might not adhere to the same constraints. The nuclear forces and the electromagnetic force might be tied to the familiar 3-dimensional space, unable to reach into the additional dimensions even if they exist. Gravity, however, influences the curvature of space itself. If the full geometry includes extra dimensions, gravity would naturally interact with them. This difference could explain why gravity appears weak. Instead of being confined, it disperses into the wider architecture. This possibility reframes how you think about gravitational behavior. Instead of asking why the force is so faint, you begin asking where it's going. The missing strength might not be missing at all. It might be spreading out into dimensions that extend beyond our awareness. From this perspective, gravity is not shy by nature. It is simply performing its role across a larger stage. Physicists studying the architecture of hidden dimensions often use visual analogies to help conceptualize what the math describes. One analogy compares our universe to a sheet suspended in a larger space. You can move around on the sheet, but not off it. The sheet represents the familiar 3 dimensions. The surrounding space represents the additional ones. The nuclear and electromagnetic forces remain stuck on the sheet, unable to reach into the surrounding space. Gravity, however, bends the sheet and the space around it. It has no reason to remain confined. That is why its effects might appear diluted. The more space there is for curvature to extend into, the less pronounced the curvature becomes in any one part of it. Another analogy compares the universe to a musical instrument. A string vibrating on a guitar has certain resonant frequencies determined by its length, tension, and shape. A drumhead has different resonances because its geometry differs. In theories with extra dimensions, the possible shapes of those dimensions determine the types of particles and forces that emerge. Hidden dimensions aren't just empty spaces, they define the rules of physics just by existing. Their size, curvature, and structure shape the characteristics of the particles that appear in our three-dimensional world. This idea helps explain why the strengths of the forces differ so dramatically. The force carriers for electromagnetism, the strong force, and the weak force might be modes of vibration that are confined to the compact dimensions or the brain representing our familiar space. Gravity, by contrast, could be a vibration that extends through all dimensions. Its energy would be spread across a larger region, making the portion visible to us appear weak. As physicists developed more refined versions of these models, they began exploring what specific shapes hidden dimensions might take. Some theories suggested they resemble tiny spheres. Others proposed shapes with complex geometrical properties. In every case, the shapes were small enough that particles moving through them wouldn't detect them as extended directions. Instead, the influence of these dimensions would show up in the form of particle masses, force strengths, and interactions. The idea that hidden dimensions shape particle properties became a central piece of high-energy physics. It turned the universe into something more like a structured environment rather than a simple container. The architecture of space determines what kinds of particles can exist, how they behave, and how forces act. The dimensions themselves become part of the machinery that generates the rules of reality. This shift in perspective has practical consequences. If hidden dimensions exist, then experiments at extremely small distances or extremely high energies might reveal deviations from the expected behavior of gravity or other forces. Physicists look for these deviations by measuring gravitational attraction between small objects at tiny distances, by studying particle collisions in accelerators, and by analysing astronomical data for signs of unusual gravitational effects. These searches continue because even small clues could reveal the shape or size of the hidden dimensions. The idea of dimensions beyond the familiar ones also influences how scientists think about the universe on the larger scales. If additional dimensions exist, they might contribute to the behaviour of dark energy or dark matter. These mysterious components make up most of the universe's mass-energy content, yet remain poorly understood. Some theories propose that dark matter could be particles interacting with the hidden dimensions. Others suggest that dark energy might be a consequence of the geometry of higher dimensional space. If true, the architecture of dimensions becomes even more central to understanding the cosmos. Thinking about these possibilities changes how you view the structure of space around you. You begin to imagine that the world might have layers or depth that are not directly visible. Every moment you move through space, you could be passing through a location where other dimensions exist curled up or folded in ways too tight to notice. The objects around you might be influenced indirectly by this hidden structure, their properties shaped by the geometry they can't move through. Gravity's faint pull becomes a subtle indicator of the wider landscape. Even though these ideas may feel unusual when first encountered, physicists view them through a practical lens. The goal is not to invent complexity, but to find models that solve persistent problems. When gravity refuses to match the strengths of the other forces, the architecture of hidden dimensions offers a possible explanation grounded in mathematics. It provides a way to unify concepts that otherwise resist connection. It gives gravity a place in the same overarching framework that describes particles and fields, while allowing it to behave differently for reasons the equations support. Understanding the architecture of hidden dimensions also offers a path toward deeper theories, such as the Gravibrane idea. If our universe is a brain embedded in a higher dimensional space, and if gravity is free to move beyond the brain, while other forces remain confined, then gravity's faintness becomes a direct result of the geometry. It is no longer a problem needing explanation. It becomes a characteristic of how the universe is built. This shift sets the stage for further exploration. Once you accept that dimensions might extend beyond the visible three, the concept of brains becomes a natural extension. brains are not abstract surfaces. In these models, they represent physical spaces where particles and forces exist. Our entire universe could be one of these brains, and gravity might be the only force that reveals the presence of the larger space surrounding it. As soon as the idea of hidden dimensions became something more than speculation, physicists needed a framework that could describe what might exist within that larger space. It wasn't enough to say the universe contains extra dimensions. Those dimensions needed structure. They needed rules. They needed something that could explain why the world you experience feels locked into 3 directions, while the mathematics suggests many more. Out of this need came one of the most surprising concepts modern theoretical physics has ever embraced: the idea of brains. A brain, short for membrane, is not a surface made of physical material. It's a mathematical description of a region of space, the kind you could move around in just like the familiar 3 dimensions you're used to. In these models, a brain is a space where particles and forces can exist. You can picture it as a sheet, not because it's literally flat, but because the analogy helps capture how it can find certain things to its surface. A brain can have any number of dimensions. A 1-dimensional brain is like a string. A 2-dimensional brain resembles a sheet. A 3-dimensional brain is more like the universe you walk through every day. And in theories that include many dimensions, brains of various types can exist together, forming a complex geometric environment. When physicists talk about a brain representing our universe, they mean that everything you know, every atom, every particle, every electromagnetic interaction, may be confined to a 3-dimensional region suspended inside a higher dimensional space. The familiar world is not the entire space. It's a slice of it, a kind of cosmic sheet floating in a larger environment known as the bulk. That term refers to the full higher dimensional space where brains can sit, move, stretch, and interact. In this picture, you can imagine our universe as one membrane among many. Other brains might exist parallel to ours, each with its own properties and perhaps its own version of physics. They could be separated from us by distances so small or so strange that no ordinary process could cross them. If these brains exist, they could form a stack, a network, or a scattered collection in the bulk. The possibilities depend on the details of whatever higher dimensional theory you adopt. The important piece is that while the familiar forces, the electromagnetic force, and the strong and weak nuclear forces are tied to our brain, gravity might not be. That single difference has enormous consequences. If the other forces cannot move off the brain, they remain tightly focused in the space you experience. Gravity, on the other hand, could extend into the bulk, spreading its influence beyond the confines of the brain. That spreading would dilute the strength of gravity on the brain, making it appear far weaker than the other forces even if its true strength in the bulk is comparable. This shift in perspective changes how you interpret the weakness of gravity. Instead of being defective or incomplete, gravity behaves differently because it has a larger environment to act in. When you feel gravity pulling downward, you're feeling only the portion of the gravitational field that remains on the brain. The rest disperses into the bulk, making gravity seem faint here, even though its full presence is spread through multiple dimensions. Physicists call this the leakage of gravity. It's not literally a substance leaking like water. It's the curvature of space extending beyond the region the other forces occupy. Thinking about brains helps clarify why the universe might appear 3-dimensional, even if it contains more. If particles and fields responsible for the strong, weak, and electromagnetic forces are tied to the brain, then your senses, which rely on those particles, would only ever detect the dimensions of the brain itself. Even if the bulk contains additional dimensions, your body, your instruments, and your entire environment would be unable to move into them. You would be like a creature living on the surface of a sheet, unaware of the space above or below, because nothing you interact with can leave the surface. The interesting part is that while you might not be able to access the extra dimensions directly, gravity can. And because gravity shapes the motion of planets, stars and galaxies, the behaviour you observe on the brain becomes a window into the structure of the bulk. Every measurement of gravitational strength, every observation of cosmic structure, every calculation involving curvature is influenced by the full dimensional landscape, even if you cannot see it. Brains become a bridge between the visible and the hidden. To get a more intuitive sense of how brains work, imagine a thin, flexible sheet floating in a larger room. If you put objects on the sheet, they move around in 2 dimensions. They can slide forward, backward, left, or right, but they cannot leave the sheet. Now imagine a heavy object placed on the sheet that makes it bend. The bending influences how lighter objects move. Even though everything is happening within the sheet, the bending occurs because the sheet exists within a larger 3-dimensional space. The sheet itself cannot straighten or bend without interacting with that surrounding space. Similarly, the gravitational curvature you observe in the universe may be shaped by how the brain interacts with the bulk. If the bulk has certain properties, if it contains fields, structures, or even other brains, gravity could behave differently in different regions. Some theories propose that gravity becomes weaker on our brain because it is attracted to another brain nearby. That attraction draws some of the gravitational field away from our brain, concentrating it elsewhere. This creates the appearance of weakness without requiring gravity itself to be intrinsically small. It's simply distributed unevenly in the bulk. Another approach suggests that the bulk may have a specific curvature that changes how gravitational fields spread. If the bulk is warped, gravity may prefer certain directions or regions. This warping could confine gravity loosely to our brain, while still allowing it to reach into the bulk. The result is gravity that feels weak but never disappears. The famous Randall-Sundrum model uses this idea to explain why gravity appears so faint on large scales, yet remains consistent with the behaviour expected from general relativity. Brains also offer a way to think about why the forces of nature appear separated. If each force is tied to a brain or a set of brains, this separation becomes a natural outcome of the structure, rather than an arbitrary difference. The strong force might be confined because its carrier particles cannot move into the bulk. Electromagnetism might remain on the brain because its fields are tied to certain dimensions that do not extend into the bulk. The weak force might behave in ways shaped by how the brain curves or interacts with fields in the bulk. This layered view transforms the universe into something more intricate than a simple 3-dimensional arena. It becomes a structured environment where different forces inhabit different regions of space. Some are confined tightly, some spread out, some interact with the bulk. Gravity's faintness becomes part of this structure rather than a mistake in the equations. The possibility of brains also opens doors to ideas about parallel universes that are more grounded in physics than in fiction. If other brains exist in the bulk, they could hold their own versions of matter, forces, and physical laws. These universes would not be separate in the sense of being unreachable by principles. They would be close in a dimensional way, but separated by boundaries the familiar forces cannot cross. Some theories even allow for interactions between brains, such as collisions or resonances, which could lead to large-scale events in the brain's histories. In certain models, the Big Bang itself could be the result of such an interaction. You don't need to adopt these far-reaching ideas to appreciate the core concept. The main point is that brains offer a structure for understanding why gravity behaves differently. They provide a space where gravity can extend its influence, while the other forces remain confined. They explain the weakness of gravity in a way that connects seamlessly to the mathematics of higher dimensions. They introduce the possibility that the universe is larger, deeper, and more layered than the part you can interact with. The concept of brains might sound unfamiliar at first, but it gives physicists something important, a framework that answers questions without conflicting with known laws. General relativity describes gravity as curvature. Quantum field theory describes particles as excitations of fields. Brains and the bulk allow these ideas to coexist in a higher dimensional environment. Gravity curves the bulk, particles remain confined to the brain, the The combination produces the universe you see. Once you accept the idea that our universe could be a three-dimensional brain suspended within a wider bulk, something about gravity starts to make more sense. It doesn't behave like the other forces because it doesn't live in the same restricted space. The others stay anchored to the brain, tied to fields and particles that cannot leave it. Gravity, however, is linked to the curvature of space itself, and if space extends beyond the brain, then gravity has no reason to remain confined. It becomes something like a traveller moving through regions the other forces cannot enter. The familiar gravitational pull you feel is just the small portion that returns to the brain after moving through the bulk. This picture helps explain why gravity appears so faint. If its influence spreads through a larger environment, the part you experience would naturally be diluted. It's the same idea as shining a light in an open area versus shining it directly onto a surface. The strength doesn't change, the distribution does. What you see depends on how much of the total energy reaches your location. With gravity, the brain receives only a part of the full gravitational field because the rest extends outward into dimensions you can't access. Thinking about gravity this way might seem unfamiliar, but it lines up with the mathematical models physicists use. In general relativity, gravity isn't a force in the traditional sense. It's the shape of space. If space has more dimensions, then gravity's shape must extend through them. The curvature caused by mass doesn't stop at the edges of the brain. It continues into the bulk just as a bend in a flexible sheet influences the surrounding space. The brain might restrict the motion of particles and fields, but the curvature doesn't vanish at the boundaries. It adapts to whatever space is available. This wandering behaviour becomes clearer when you think about how gravity acts across distances. The nuclear forces are short range. Electromagnetism can extend far, but only if charges don't cancel out. Gravity, by contrast, keeps going. Its pull never drops to zero, no matter how far it reaches. If gravity were confined strictly to the brain, its behaviour might resemble the other forces more closely. But because it interacts with the wider geometry, its reach becomes unlimited. The strength weakens with distance, but the influence never stops. That endless reach hints at its ability to move through more space than you can directly observe. One way physicists describe this is by saying that the gravitational field lines don't remain neatly on the brain. They spread outward into the bulk, allowing gravity to roam. The brain bends under the influence of mass, but the curvature doesn't remain confined. It ripples outward. The more directions the curvature can extend into, the thinner it appears in any single region. You're left with a gravitational force that feels gentle even when the masses involved are enormous. This helps clarify why planets orbit stars instead of colliding into them. The gravitational pull they feel is enough to guide their motion, but not strong enough to pull them inward rapidly. The balance between gravitational attraction and orbital momentum exists partly because gravity acts as a traveller. It spreads through the bulk, giving the brain only a fraction of the total curvature. In a universe where gravity didn't extend into extra dimensions, the numbers would look very different. Planetary orbits would require different speeds. Stellar formation might occur differently. The entire structure of cosmic evolution would change. Physicists often compare this wandering nature to a kind of leakage. Not leakage in the sense of something escaping by accident, but leakage as a consequence of how space behaves. If the brain exists inside a higher dimensional space, then gravity automatically occupies the full environment. It doesn't choose to wander. It simply follows the geometry. The curvature created by mass spreads in all available directions. Because the other forces are confined to the brain, they maintain their strength. Gravity alone distributes itself more widely. This distribution also makes sense when thinking about the Planck scale, the energy level where quantum gravitational effects become important. The Planck scale is extraordinarily high because it reflects the full strength of gravity across all dimensions. The portion you measure on the brain is much lower. This mismatch explains why quantum gravity is so hard to study experimentally. you're only seeing a reduced version of the force. The true scale exists in the bulk, out of reach of particle accelerators limited to the brain. As researchers explored this idea further, they realized that the traveller analogy isn't just a way of visualizing gravity, but a necessity of the models themselves. In theories with extra dimensions, gravitational waves are not restricted to the brain, they can pass through the bulk. In some versions, the waves spread unevenly depending on the shape of the bulk. If the bulk is flat, the waves spread freely. If the bulk is warped, they curve along specific paths. The details depend on the model, but the key idea remains the same. Gravity does not stay put. This wandering raises interesting questions. If gravity moves through the bulk, could it interact with other brains if they exist? Some theories say yes. If another brain lies close to ours in the bulk, gravity could pass between them. The interaction might be faint, but it could exist. In that case, gravity on our brain might be influenced partly by matter on a neighbouring brain. You would never see that matter directly because the other forces can't cross brains, but gravity could feel it. This creates the possibility that some of the gravitational effects we observe might include contributions from unseen matter on a nearby brain. While this idea remains speculative, it illustrates how the wandering nature of gravity changes the way physicists think about the universe. Instead of assuming that all gravitational effects originate on our brain, they begin considering the possibility that the bulk contains additional sources. The universe becomes a layered environment where gravity moves freely between regions while everything else remains confined. The wandering behaviour also offers a new way to understand the evolution of the universe. In many models, the early universe was hot and dense enough that the distinction between brain and bulk wasn't as sharp. Gravity might have interacted more strongly with the brain at high energies. As the universe expanded and cooled, the interactions changed, leaving gravity more spread out. This shift could explain why the force appears so weak today compared to the early conditions. It's not that gravity changed strength, it's that the environment changed, altering how the curvature distributed itself. One of the more intriguing aspects of this wandering nature is its potential connection to the hierarchy problem. If gravity's weakness on the brain is a direct result of its ability to travel through the bulk, then the enormous difference between the strengths of the fundamental forces is no longer a mystery. The nuclear and electromagnetic forces appear strong because they're stuck on the brain. Gravity appears weak because its influence extends into places the others cannot reach. The difference is not a fundamental imbalance, but a consequence of dimensional architecture. This perspective reframes the entire conversation about force strengths. Instead of asking why gravity is weaker, you begin asking why the other forces are confined. What mechanisms tie them to the brain? In string theory, the confinement emerges naturally because the particles associated with these forces are open strings with endpoints stuck to the brain. Gravity's carrier, the graviton, is a closed string with no endpoints. It doesn't attach to the brain. It can move freely into the bulk. That difference in string structure provides a possible explanation for why gravity wanders while other forces remain localized. Even if you don't adopt string theory directly, the idea that forces can be tied to specific regions helps build a coherent picture. The traveller analogy becomes even more compelling when you think about how gravitational waves behave. When they pass through space, they carry information about the curvature changing over time. If the bulk contains roots or regions that alter how these waves move, the waves might not stay strictly on the brain. Some of their energy could leak into the bulk. In certain models, this leakage would make gravitational waves appear weaker or reduce their amplitude as they travel long distances. Detecting such deviations could offer clues about the structure of the bulk. Although current measurements cannot confirm or refute these ideas, they provide a framework for future exploration. The wandering behaviour of gravity creates predictions that can be tested as technology improves. Physicists look for small deviations from Newton's law at short distances, where extra dimensions might reveal themselves. They analyse gravitational wave data for signs of energy loss into the bulk. They study cosmological data for evidence that gravity interacts with regions beyond the brain. This ongoing search reflects how central gravity's wandering nature is to the broader picture. It's not a minor detail or a mathematical curiosity. It's a potential key to understanding the universe's structure. If gravity truly behaves as a traveller, then the world you experience is only part of the full environment. The brain becomes a local region in a larger space. The forces you interact with daily are confined to this region, but gravity connects it to the wider landscape. As you let this idea settle, it's natural to wonder what the bulk actually looks like. If gravity travels through it, the bulk must have shape, curvature, and structure. It might hold fields that influence how gravity behaves. It might contain other brains with their own physical realities. It might be warped, flat, or dynamic. The details depend on the theory, but the important point is that gravity doesn't limit itself to the brain. Its presence in the bulk shapes the physics you observe. Once the idea of gravity as a traveller becomes familiar, the next question forms almost automatically. If gravity can move through the bulk, why does it do so? What makes this force different from the others in a way that allows it to slip into dimensions the strong, weak, and electromagnetic forces cannot access? And why would the universe be shaped in a way that encourages this behaviour rather than preventing it? These questions arise not because the models require speculation, but because the mathematics and observations consistently hint that gravity has more freedom than the forces confined to the brain. To understand why gravity might leak into other dimensions, it helps to start with the difference between how forces arise in quantum field theory versus in general relativity. The nuclear and electromagnetic forces are described using particles that carry interactions. They behave like messenger particles that relay influence between other particles. Those messengers move through fields tied to the brain. They require specific structures to exist, and those structures depend on the dimensions the brain provides. Since those forces emerge from the brain's internal fields, they remain confined to it. Gravity, however, isn't a messenger force in the same way. It's not fundamentally an exchange of particles, even though some models introduce gravitons for the sake of unification. Gravity emerges from the curvature of space-time. Anything with mass or energy bends space-time, and objects follow paths determined by that curvature. If space-time has more dimensions, then the curvature has more directions to extend into. Gravity simply follows the shape available to it. This is the root of the idea that gravity leaks. It is responding to the full geometry rather than the portion of geometry defined by the brain. This difference becomes clearer if you think about how surfaces behave when embedded in larger spaces. Imagine a flag stretched in the wind. The fabric is two-dimensional, but every bend or ripple in the flag occurs because air pushes it within a three-dimensional space. The bending isn't part of the fabric alone, it's part of the surrounding environment. In a similar way, if our universe is a brain within a higher dimensional space, the curvature that creates gravity is shaped by the bulk as well as by the brain. The brain restricts particles to its surface but cannot restrict curvature completely. The curvature can extend beyond its boundaries, creating a gravitational field that reaches into other dimensions. Another reason gravity might leak involves how mass interacts with the bulk. In brain-world models, mass and energy on the brain produce curvature in the bulk. This curvature isn't confined, it spreads. The more dimensions there are, the more directions the curvature can spread into. Because the gravitational field lines disperse through all available dimensions, the fraction that remains on the brain becomes smaller. This dilution explains why gravity appears weak compared to forces that stay confined to the brain. This idea isn't just a convenient explanation. It's a consequence of the equations used to describe higher dimensional space. When physicists write down the math, describing curvature in dimensions beyond 3, the solutions show that gravity's influence becomes distributed. The familiar inverse square law, which describes how gravity weakens with distance, changes slightly when extra dimensions are involved. At small scales, gravity might become stronger than expected because it hasn't spread through the extra dimensions fully yet. At larger scales, the dilution becomes significant, making gravity appear faint. Experiments have been designed to look for this shift. Researchers test gravity at tiny distances to see if it deviates from Newton's law. If it becomes stronger at short distances, that could be a sign of extra dimensions. So far, no deviation has been detected, but the experiments reach only limited scales. The dimensions could be smaller than those experiments can probe. The possibility remains open because nothing observed rules it out. The idea that gravity might leak also gains strength from the problem of unification. The strong, weak, and electromagnetic forces unify at high energies in certain theories. Their strengths converge, forming a consistent pattern. Gravity, however, sits far outside this pattern. Its strength is so low that it doesn't join the others unless you assume something dramatic changes at extremely high energies. If gravity is diluted by spreading into other dimensions, then its true strength in the bulk might be much higher. The tiny force you feel on the brain becomes only a fraction of the full interaction. Under that assumption, the full strength of gravity could align with the other forces at high energy, but only if you consider the bulk. On the brain alone, the numbers look mismatched. In the bulk, they look connected. This provides a potential solution to the hierarchy problem, the puzzle describing why gravity is so much weaker than the other forces. The hierarchy disappears if gravity leaks. The difference in force strengths becomes a geometric effect rather than a fundamental physics imbalance. You no longer have to explain why gravity is weak. You explain why the brain only receives a diluted version of a stronger gravitational field that acts in more dimensions. The mismatch becomes a consequence of dimensional structure rather than a flaw in the laws of nature. There's another perspective as well, one that emerges from string theory. In many versions of string theory, particles are described as strings that can vibrate in different ways. Open strings, which have endpoints, often attach to brains. Those endpoints limit the motion of particles produced by open strings, confining them to the brain. That includes particles responsible for the electromagnetic and nuclear forces. Gravity, however, is described by closed strings. These strings form loops without endpoints. Because they have no endpoints that lock them onto the brain, closed strings can move freely into the bulk. The graviton, the hypothetical particle that carries gravitational interactions in quantum versions of gravity, is associated with these closed strings. That difference alone provides a reason gravity can move through extra dimensions. Even if string theory isn't adopted directly, this idea helps visualize why gravity behaves differently. The forces produced by open strings remain confined. The force produced by a closed string does not. This structural difference mirrors the behavioral difference observed in the forces. Gravity leaks because the thing responsible for carrying it isn't attached to the brain. One of the most interesting consequences of this leakage is the possibility that gravity interacts with fields or particles in the bulk that the other forces never touch. Those fields might shape the behavior of gravity on the brain, making it appear weaker, stronger in certain regions, or modified in ways that could be detectable. If gravity interacts with things in the bulk that aren't part of the standard model of particle physics, then measuring gravitational behavior might reveal information about hidden aspects of the universe. Another reason gravity might leak involves the shape of the bulk itself. In some models, the bulk is warped. The warp changes how gravity moves through the space. It can either draw gravity towards certain regions or push it away. If our brain sits in a specific region of this warp, gravity might be partially confined but not fully. Some of the gravitational field remains near the brain, while some extends further out. This partial confinement appears to weaken gravity on the brain. If the warp changes over large distances, gravity might appear stronger or weaker in different regions of the universe. This could have implications for cosmology, influencing how galaxies form or how the expansion of the universe behaves. Some versions of these ideas connect directly to dark energy or dark matter, suggesting that gravity's interaction with the bulk might contribute to those unexplained phenomena. All these reasons, curvature spreading through extra dimensions, brain confinement, closed string motion, warped geometry, create a unified picture in which gravity's leakage becomes natural rather than unusual. Instead of struggling to explain gravity's faintness, the theories suggest that faintness is exactly what you would expect if gravity operates in a space larger than the one you experience. One way to visualize this is to imagine a speaker placed against a wall. The sound you hear on one side of the wall is only part of the total sound waves being produced. Most of the sound spreads into the room on the other side. The wall blocks some of it, absorbs some, and lets some through. The sound that reaches you feels faint because you are only receiving a fraction of the energy. On the other side of the wall, the sound might be loud and clear. Gravity might be similar. The gravitational field in the bulk could be much stronger or more structured, but the brain receives only the fraction that bends back into its space. Even though you cannot detect the bulk directly, gravity gives clues about its presence. When you see how weak gravity is, how hard it is to detect between small objects, how easily it is overshadowed by the other forces, you begin to suspect that gravity is influenced by something beyond the brain. The leakage is not an odd behaviour, it's a sign that the environment is larger than what the other forces reveal. Thinking about gravity this way changes how you interpret many familiar observations. When planets orbit a star, you're seeing the gravitational field that remains on the brain. When gravitational waves travel through the universe, you're seeing the on-brain portion of a signal that may extend far into the bulk. When black holes bend light, you're observing the part of the curvature that pushes back into the brain. All of these effects become small pieces of a larger picture in which gravity interacts with a wider space than the other forces. As conversations about gravity leaking into extra dimensions became more detailed, physicists started asking a deeper question. If gravity spreads into the bulk, what exact structure guides that motion? It wasn't enough to say gravity escapes into higher dimensions. The models needed something more specific, something that could describe how gravity interacts with the brain, how it behaves as it travels through the bulk, and why it returns to the brain in the weakened form we observe. Out of those needs grew the Gravibrane concept, an idea that treats gravity not just as a wandering presence, but as a force shaped by a particular geometric relationship between the brain and the bulk. The Gravibrane idea is not a single fixed model with rigid boundaries. It's more like a family of models that all share a common theme. Gravity occupies a bridge-like role connecting the familiar three-dimensional world to the deeper dimensional landscape beyond it. In these models, the brain acts as a host for ordinary matter and the familiar interactions, while the bulk provides a vast space in which gravity can extend, disperse, and reshape itself. Between these two regions sits the Gravibrane, a conceptual structure that makes sense of how gravity moves between worlds. It is not a wall, not a barrier, but a kind of soft interface, a region where gravity transitions smoothly from being a brain-bound influence to a higher dimensional one. If you picture the brain as a sheet suspended in a larger room, the Gravibrane is the region where the sheet meets the air around it. It's not a sharp dividing line, but a gradual blending. The sheet represents your familiar space, the air represents the bulk. Gravity behaves like the bending of the sheet, but also like a breeze that moves through the room. In the region where sheet and air meet, the bending of the sheet merges with the airflow. That transitional region is similar to what physicists imagine the Gravibrane to be like. It's a place where the gravitational field is neither fully on the brain nor fully in the bulk, but interacting with both environments. To make this more concrete, consider how gravitational waves behave. When large masses such as black holes collide, they send ripples through space-time. If space-time has additional dimensions, some of that wave energy can travel into the bulk, but not all of it leaves the brain. The Gravibrane acts as a guiding interface. allowing part of the wave to remain in the brain while the rest disperses into the bulk. This split explains why gravitational waves become harder to detect over long distances. They're losing some of their energy into regions beyond the brain. The Gravibrane helps determine how much stays and how much leaves. Because of this bridging behaviour, the Gravibrane becomes a central concept for understanding gravity's faintness. If gravity is pulled both toward the brain and toward the bulk, the balance between these pulls determines how strong gravity appears in the familiar 3 dimensions. The brain holds part of the gravitational field close, but the bulk offers so much extra room that gravity inevitably spreads. The Gravibrane doesn't confine gravity like a container, it channels gravity, shaping how it moves without restricting its freedom. In doing so, it creates a natural explanation for why gravity is diluted. One way to think about this is by imagining a large sheet floating on water. If you tap the sheet gently, the vibration spreads across the sheet, but some of the energy transfers into the water below. The water carries away part of the motion. The sheet continues vibrating, but the waves are smaller than they would be if the water weren't there. In this analogy, the sheet is our brain, the water is the bulk, and the interface between them is the Gravibrane. Gravity behaves like the vibration. It acts strongly in the bulk, but when it interacts with the brain, the on-brain portion is weaker because some of the energy has flowed into the bulk. This helps clarify why gravity's strength on the brain looks so different from the other forces. Electromagnetism and the nuclear forces don't have an equivalent interface. They don't interact with the bulk. They remain trapped within the brain, unable to leak energy away. Their strengths reflect the full energy of their fields. Gravity, however, experiences drainage. It loses part of its presence into the bulk. The amount it loses depends on the geometry of the Gravibrane. If the Gravibrane allows a lot of gravitational energy to pass through, gravity appears very weak on the brain. If it restricts the flow moderately, gravity appears stronger. The observed faintness suggests that gravity has a wide range of motion in the bulk, not a narrow one. The Gravibrane also shapes how particles interact with gravity. In many models, matter is confined to the brain, but gravity interacts with matter through the Gravibrane. That means matter curves the brain, and the curvature affects the Gravibrane, which in turn bends the bulk. The combined curvature creates the gravitational field you observe. Since the brain and the Gravibrane work together to transmit this curvature into the bulk, the resulting field is more dispersed than it would be if space had no additional dimensions. Think of it as a message travelling through 2 different media. The message begins on the brain when mass bends the familiar 3-dimensional space, but the message continues into the Gravibrane, where the bending is partially redirected into extra dimensions. The farther the curvature spreads, the less of it remains concentrated in the brain. That dilution is what you measure whenever you observe gravity acting on planets, objects, or bodies. You're sensing the portion of the message that remains after it has passed through the Gravibrane. There is another subtle aspect to this idea. The Gravibrane isn't just a passive interface. It can have properties of its own. Depending on the model, the Gravibrane might have tension, thickness, or curvature. It might be flat or warped. These properties affect how gravity moves. If the Gravibrane has high tension, it could resist certain directions of curvature, guiding gravity more strongly back toward the brain. If it has low tension, gravity might more easily slip into the bulk. In some theories, the Gravibrane is thick enough that gravity can move within it, before deciding whether to return to the brain or escape into the bulk. That thickness acts like a buffer zone, shaping how much gravity remains near the brain and how much spreads outward. The idea of thickness becomes important because it means the brain isn't a thin surface, it's a region with internal structure. Even though you experience the brain as a 3-dimensional world, models often treat it as having small but finite depth. Within this depth lies the Gravibrane structure. Gravity travelling from the brain into the bulk must pass through this region, and the properties of that region determine how gravity transitions between dimensions. This is one reason the Gravibrane is described as soft rather than rigid. It bends, fluctuates, and interacts with the gravitational field in ways that aren't binary. Gravity doesn't simply leave or stay. It gradually shifts from one environment to another. Because of this smooth transition, the Gravibrane also provides a natural way to think about gravitational resonance. In some models, gravity can resonate between the brain and the Gravibrane, producing oscillations that affect how gravity behaves at different scales. These resonances may explain why gravity is so weak on small scales, but grows more pronounced at larger ones. The idea is that gravity tries to localize on the brain but is constantly drawn into the bulk, creating a dynamic balance. The Gravibrane mediates this balance, absorbing part of the curvature and releasing part of it back toward the brain. This dynamic view of gravity is one reason the Gravibrane concept gained attention. It not only explains gravity's faintness, but also offers a way to connect gravitational behavior to the geometry of the bulk. If the bulk is curved, the Gravibrane must adapt to that curvature. If the bulk contains fields or structures, the Gravibrane interacts with them. These interactions influence gravity on the brain, meaning the behavior of gravity in your world contains information about the deeper structure of the universe. This perspective becomes particularly interesting when thinking about cosmology. If the Gravibrane interacts with structures in the bulk, it might play a role in phenomena such as cosmic inflation or the expansion of the universe. Some models propose that the energy driving the expansion resides partly in the bulk, affecting the brain through the Gravibrane. Others suggest that the Gravibrane could help explain dark energy by altering how curvature spreads between dimensions. While these ideas remain speculative, they show how a soft interface between the brain and bulk could influence large-scale cosmic behavior. The Gravibrane concept also provides room to think about the possibility that other brains exist nearby. If another brain lies close to ours in the bulk, the Gravibrane might serve as a medium through which gravity from that brain influences ours. This means gravitational effects observed in our universe might include contributions from mass on another brain. In this interpretation, gravity becomes a shared property of multiple brains, with the Gravibrane acting as the linking region. You wouldn't detect matter on another brain through electromagnetic or nuclear forces, because those forces don't cross brains. But gravity does. If gravity is influenced by mass on a neighbouring brain, that influence reaches us through the Gravibrane. This possibility changes how you think about missing mass in the universe. Some of the gravitational effects attributed to dark matter might be gravity from another brain interacting with ours through the Gravibrane. Although this idea is not the standard explanation for dark matter, it shows how higher dimensional models create new possibilities for interpreting gravitational anomalies. Even if the Gravibrane is only a theoretical construct, it offers a way to imagine how gravity connects different layers of reality. Thinking about the Gravibrane also helps bridge concepts from general relativity and quantum theory. In general relativity, gravity is curvature. In quantum theory, forces are interactions between particles. The Gravibrane sits between these descriptions. It connects curvature in the bulk to interactions on the brain. It mediates between geometric and particle-based views of gravity. This makes it a useful conceptual tool for exploring how quantum gravity might work. What makes the Gravibrane idea compelling is not that it explains everything, but that it provides a natural setting for gravity's unique behaviour. It allows gravity to be both strong and weak depending on where you measure it. It allows gravitational fields to be both localized and extended. It allows gravity to be a mediator between the brain and the bulk without breaking the known laws of physics. The Gravibrane becomes part of the landscape, shaping how the universe behaves at fundamental scales. By the time gravity is understood as something that can drift between the brain and the bulk, it becomes natural to wonder how its motion shapes the signals it sends through space. Every shift in mass creates a disturbance in the gravitational field. These disturbances aren't like sound waves travelling through air or ripples gliding across water, although those analogies can help you imagine the idea. They are changes in the curvature of space-time itself, spreading outward at the speed of light. And because space-time might have more dimensions than the familiar 3, the ripples might not stay entirely within the brain. They might extend into the bulk, moving through directions you can't see, feeling the shape of spaces your senses cannot touch. The idea of gravitational waves isn't new. They were predicted long before anyone could detect them. Einstein's equations of general relativity described gravity not as a force but as geometry, and those equations allowed for waves, tiny variations in curvature that travel outward when massive objects move or collide. But predicting their existence was different from observing them. The waves are extraordinarily faint by the time they reach Earth. They stretch and compress space by an amount so small that even the most sensitive detectors struggle to measure it. The faintness would be true even in a universe without extra dimensions, but in a higher dimensional world the faintness becomes even more understandable, because part of the wave might be travelling into regions beyond the brain. Before gravitational waves were detected, scientists wondered whether gravity truly behaved like a field that could vibrate the same way a string can vibrate. They wondered whether the waves could reveal something about the hidden structure of space. And they wondered whether the faintness of the waves was simply due to distance, or whether something more fundamental was happening. When the first detection finally came, it confirmed the idea that the ripples existed, but it didn't settle the question of whether the waves were confined to the brain. To understand how gravitational waves connect to the idea of higher dimensions, it helps to think about what happens when two massive objects spiral toward each other. As they orbit, the curvature of space-time around them changes. When they collide, the curvature shifts dramatically, producing an intense burst of gravitational wave energy. In three-dimensional space, that energy spreads outward like ripples in a pond, weakening as it travels. But if the waves can move into the bulk, then the outward spread occurs through more directions. The energy doesn't just dilute across the surface of the pond, it dilutes through a larger volume. This additional spreading changes what someone on the brain can detect. The gravitational wave that reaches you has already been weakened by the distance it travelled, and by the dilution into extra dimensions. That double reduction explains why gravitational waves are so faint, and why detecting them required such precise instruments. You're sensing a portion of a signal that exists more fully in the bulk. The brain receives only the part of the curvature change that remains inside its dimensions. This is where the idea of strings becomes relevant. In string-based models of physics, particles are described as tiny vibrating strings. Different vibrations produce different particles. A string vibrating one way might represent a photon. A different vibration might represent an electron. Closed strings, which form loops, can move through the bulk. Open strings, which have endpoints, remain attached to the brain. Gravity, associated with closed strings, can move through extra dimensions. Forces like electromagnetism, associated with open strings, cannot. When people talk about strings, they often imagine strands of energy or tiny loops floating in space. But what matters most in this context is that the gravitational field arises from vibrations that aren't tied to the brain. These vibrations can produce not only particles but also waves, gravitational ripples that travel through the dimensional structure. The string perspective helps make sense of why gravitational waves might disperse into the bulk. The wave is a pattern of vibration. If the vibration belongs to a closed string, it has freedom to move into the bulk. The wave follows that freedom. Even if you don't adopt string theory directly, the key idea remains the same. Gravity doesn't stay confined. Its ripples, like its static curvature, spread through the full dimensional environment. That spreading is what allows models involving extra dimensions to remain consistent with observed gravitational behaviour. Instead of being an unnecessary complication, the possibility of gravitational leakage helps explain why gravity is difficult to measure on small scales, and why the gravitational field seems so weak compared to the other forces. As researchers explored the patterns produced by gravitational waves, they realised that the waves could reveal clues about the bulk. If gravitational waves lose energy into the bulk, their amplitude on the brain should decrease slightly more rapidly than predicted by three-dimensional models. The difference would be small, but measurable. If the waves resonate differently because of bulk geometry, That resonance could create subtle patterns in the wave signal. Scientists began looking for such patterns. Although current detections don't show clear evidence of extra-dimensional behaviour, the waves detected so far come from distances that aren't large enough to reveal the differences clearly. Future detections, especially those from extreme distances or early universe events, might reveal the signs researchers are looking for. But gravitational waves aren't the only ripples that matter here. The idea of vibrating strings and fluctuating branes also creates patterns in space. In some models, the brain itself can fluctuate like a surface, trembling in a larger ocean. These fluctuations act like waves inside the brain, influenced by the bulk. They reshape how gravity and matter interact. When the brain fluctuates, the gravibrane, the soft interface connecting the brain and the bulk, shifts as well. These shifts change how easily gravity leaks into the bulk and how much returns to the brain. In this picture, gravity doesn't simply leak through static boundaries. It interacts with a dynamic environment. The gravibrane acts like a flexible layer that can bend, oscillate, and stretch. When the brain vibrates, it pulls on the gravibrane. When the gravibrane vibrates, it influences how the gravitational field spreads through the bulk. The entire system becomes a complex interplay of waves moving between regions. The behavior of gravity becomes a continuous flowing pattern shaped by interactions at multiple levels. This dynamic picture also allows for the possibility that gravity waves can resonate with the structure of the hidden dimensions. If the bulk has a specific shape, certain wave frequencies might propagate more easily into it, others might reflect back toward the brain. In this sense, gravity waves could act like sound waves inside a chamber, responding to the shape of the room. The hidden dimensions might influence which frequencies remain on the brain and which escape. Detecting such patterns would give physicists direct information about the geometry of the bulk. At this point, it becomes useful to think about curved space itself as something that can resonate. Space is not rigid. It bends and stretches in response to mass and energy. When gravitational waves pass through space, they cause tiny, rhythmic shifts. These shifts can reveal how many directions space has, how those directions are curved, and how easily waves pass from one region to another. Gravity becomes something like a probe, sampling the shape of both the brain and the bulk with each ripple it sends out. Even on small scales, the idea of curved space resonates with the idea of strings. If particles are vibrating loops, then their vibrations influence curvature, and if curvature influences those vibrations, the system becomes coupled. Gravity interacts with matter through these vibrations. The waves it carries encode information about the stresses, strains, and shapes of the environment. When the environment includes extra dimensions, the waves encode information about those dimensions as well, even if the details are difficult to extract. In higher dimensional models, the gravitational field is described not just by curvature, but by the behavior of specific modes. Modes are patterns of vibration or oscillation that depend on the structure of the space. Just as a musical instrument can support certain notes depending on its size and shape, the bulk can support certain gravitational modes. Some of these modes stay close to the brain, others extend far into the bulk. The modes that stay near the brain are what you experience as ordinary gravity. The modes that extend into the bulk are responsible for gravity's dilution. What makes this idea powerful is that the modes provide a natural mechanism for explaining why gravity behaves differently at different scales. On small scales, local curvature dominates. On larger scales, the bulk structure influences how gravity spreads. The more you think about the modes, the more you see gravity as a layered phenomenon, shaped by multiple environments at once. These ideas come together when thinking about the faintness of gravitational waves, the weakness of everyday gravity, and the structure of strings. Everything connects back to the idea that gravity's signals, its ripples, are spread through more space than the other forces, that its carriers are free to move beyond the brain, and that the gravibrane mediates this movement. gravity becomes a force that reveals the shape of space not through direct observation, but through how its ripples behave. As ideas about gravity spreading through the bulk became clearer, physicists naturally wondered where in the universe this behaviour might be most visible. Ordinary space doesn't reveal much. The gravitational field from a planet or a star is gentle and familiar. The waves that pass through space are faint and difficult to detect. The curvature around everyday objects doesn't distort the brain or the gravibrane strongly enough to expose the deeper architecture. But some objects do push gravity to extremes, compressing mass into regions so dense that the curvature becomes intense. These objects behave like natural amplifiers of gravitational behaviour, bending space in ways that no laboratory experiment could ever reproduce. Among them, black holes stand out immediately. A black hole is not a hole in the traditional sense. It is a region where mass has collapsed to such a small volume that the curvature of space-time becomes steep enough to prevent even light from escaping. Although black holes are often described as regions of extraordinary gravity, it's more accurate to say they represent extreme curvature. The distinction matters because curvature involves the full geometry, not just the strength of a force. If gravity interacts with extra dimensions, then the curvature created by a black hole should also interact with them. This makes black holes important windows into whatever lies beyond the brain. When people imagine black holes, they often picture spheres of darkness surrounded by swirling disks of matter. That image helps visualize the event horizon, the boundary where anything crossing it can no longer return. But the real importance of the event horizon is how it shapes the gravitational field. Near the horizon, the curvature becomes so steep that small differences in position create large differences in the paths objects follow. In a three-dimensional world, the horizon marks the limit of return. In a higher dimensional world, the curvature might extend differently, creating shapes in the bulk that you cannot see but that influence gravity on the brain. This idea leads to an important realization. If black holes exist on the brain, then the curvature they create must extend into the bulk. The gravitational field around a black hole is not restricted to the brain's surface. It spreads, just like all curvature spreads. But because the curvature near a black hole is much stronger than ordinary curvature, it can probe deeper into the bulk. In a sense, black holes are the strongest gravitational emitters available, and the patterns they produce can reveal how many directions gravity can spread through. One way researchers explore this idea is by thinking about the shape of the horizon. In three-dimensional space, the event horizon of a non-spinning black hole is spherical. But in higher dimensional models, the shape changes. It might stretch, flatten, or warp depending on how the bulk is curved. These distortions don't change the appearance of the horizon on the brain, but they change the full shape that gravity interacts with. If the bulk has additional dimensions, the horizon may extend into them. This creates a higher dimensional object that includes the familiar three-dimensional horizon as a sub-region. Observers on the brain cannot see the full structure, but gravity responds to it. Thinking about the horizon in this way helps explain why black holes could act as probes of higher realms. When a black hole forms, the curvature it creates spreads into every dimension available. If the curvature interacts with the gravibrane, the black hole becomes a point of connection between the brain and the bulk. It doesn't open a passageway in the sense of a tunnel. Instead, it becomes a location where gravity reaches deeply into regions that ordinary matter never touches. The brain might bend near the black hole, and the gravibrane might respond to the intense curvature. These changes could influence the gravitational field that returns to the brain, creating subtle deviations from predictions based on a purely three-dimensional world. One of the earliest clues supporting this idea came from attempts to understand how black holes evaporate. Stephen Hawking showed that black holes can lose mass through a process known as Hawking radiation. According to this concept, particle-antiparticle pairs form near the horizon. One falls into the black hole while the other escapes, carrying energy away. In a three-dimensional world, the evaporation follows a predictable pattern. But in a higher dimensional world, the pattern changes because the horizon's shape changes. The evaporation depends on how many dimensions the curvature can spread into. If the bulk has more space for curvature, the black hole might evaporate differently. This difference becomes particularly important for small black holes. Large black holes have horizons so broad that the extra dimensions might not significantly influence their evaporation. Small black holes, however, have horizons that approach the size of the extra dimensions. If the dimensions are compact, a small black hole could sense their size. The evaporation could increase or decrease, depending on how the gravibrane and the bulk interact. Although such small black holes haven't been observed, the idea shows how gravity's behaviour depends on the environment beyond the brane. Another reason black holes act as windows into hidden realms involves the distribution of gravitational modes. In higher dimensional models, gravity is described by multiple modes, some of which stick to the brane while others extend into the bulk. The modes that stay near the brane create the familiar gravitational force. The modes that extend into the bulk weaken gravity on the brane. Black holes, by producing intense curvature, can excite a wider range of modes. This means black holes might radiate gravitational energy into the bulk more easily than ordinary objects. If some of that radiation escapes the brane, it reduces the amount of gravitational energy that remains in the brane. Observers would see the black hole evolving slightly differently than predicted by models without extra dimensions. This is not speculation pulled from imagination. It emerges from the equations themselves. When physicists solve the Einstein field equations in higher dimensional space, they find that gravitational radiation behaves differently near strong curvature. Some models show that black holes emit gravitational waves into the bulk much more efficiently than larger, less curved regions. Others show that the waves become trapped near the brane, depending on the Gravibrane structure. Either way, the interaction reveals information about the dimensions. The black hole becomes an amplifier for the properties of the bulk. The motion of matter near black holes also provides clues. When material falls inward, it heats up and emits radiation. In a three-dimensional universe, the radiation follows predictable spectra. In a higher dimensional universe, the radiation changes slightly because the curvature affects how matter moves. Even though the differences might be tiny, they exist in principle. If instruments become sensitive enough, these differences could reveal whether gravity interacts with extra dimensions. Researchers study accretion disks, the swirling structures of matter falling toward black holes for this reason. The patterns of motion in the disk depend on the curvature around the black hole, and the curvature depends on the dimensional structure. Another interesting idea comes from thinking about black holes on the brane versus black holes off the brane. In most models, matter is confined to the brane, so black holes formed from collapsed matter must begin on the brane. But the curvature they create might not remain there. A black hole could have a horizon that extends into the bulk. This means part of the black hole exists in the brane and part exists beyond it. In such a case, the black hole's full shape includes regions the brane cannot detect. Observers on the brane would see only a portion of the horizon. The rest would lie in the bulk. This idea leads to a concept known as a tidal black hole. A tidal black hole is a black hole that feels the gravitational influence of a nearby brane or structure in the bulk. Its shape reflects not only the curvature caused by mass on the brane, but also the curvature created by objects in the bulk. You wouldn't detect those objects directly through electromagnetic or nuclear forces, but gravity would reveal them by shaping the black hole. In this way, black holes act like mirrors reflecting the structure of the bulk. The reflection isn't visual, it's encoded in how gravity behaves. The idea extends even further. If another brane lies close to ours, matter on that brane could also form black holes. Those black holes would not appear visibly in our universe, but their gravitational fields might influence our brane. The gravibrane mediates the connection. A black hole on another brane could shape the bulk in ways that bend the gravibrane and alter gravity on our side. Observers might see small gravitational anomalies without any visible source. Although this idea remains theoretical, it shows how higher dimensional models change the way physicists think about invisible mass and unexplained gravitational behaviour. Some researchers have even proposed that microscopic black holes could be created in high-energy collisions if the extra dimensions are large enough. These black holes would evaporate almost instantly, but their evaporation patterns would reveal the dimensional structure. The higher the number of dimensions, the faster the evaporation. Although no such black holes have been observed, the search for them continues because they would provide direct evidence for extra dimensions. In all these cases, the common theme is that black holes push gravity to limits where the hidden structure of space becomes relevant. Strong curvature interacts with the gravibrane differently than weak curvature does. Intense gravitational waves spread differently through the bulk than faint waves do. The shapes of horizons change in ways that reveal the geometry of the hidden dimensions. Black holes are not mysterious because they hide matter. They are important because they reveal the shape of space. Their role becomes even more interesting when thinking about how black holes interact with the expanding universe. In a universe with extra dimensions, the expansion might influence black holes differently. The brane could stretch, and the gravibrane could shift, altering the curvature near black holes. These changes might produce patterns in gravitational waves that reflect the expansion of the brane in the bulk. Observing such patterns could reveal how the brane evolves over time. As the idea of gravity touching more dimensions became familiar, the question that launched much of this exploration settled into clearer focus. If gravity truly spreads into the bulk, and if the gravibrane helps channel part of its strength away from the brane, then the extraordinary weakness of gravity in everyday life might not be a flaw or an oddity. It might be a direct result of the universe's architecture. But even after following the idea from the structure of branes to the role of black holes, the puzzle still lingers in a way that invites careful attention. The weakness of gravity isn't just a curiosity. It's one of the biggest inconsistencies in the known forces of nature, and its presence shapes nearly everything about the universe. The missing strength appears in countless everyday experiences. You can lift a paperclip with a small magnet, overcoming the gravitational pull of an entire planet. A tiny charged object can draw in dust, or push it away with ease while gravity struggles to compete. The strong nuclear force binds protons and neutrons together inside atoms, overpowering the electric repulsion between their charges. The weak nuclear force quietly changes particles in reactions that power the sun. All of these forces operate at strengths far above gravity's. Gravity's influence appears only when enormous masses are involved, and even then it is never overwhelming. Stars hold planets in orbit, but the balance is delicate. Galaxies form structures through gravity, but the force remains subtle compared to the energies involved in nuclear or electromagnetic processes. This imbalance is known as the hierarchy problem. The name implies a ladder of strengths with gravity at the bottom, far below the other forces. The difference is enormous, so large that explaining it requires more than a simple adjustment in equations. The numbers differ by many orders of magnitude. Physicists tried for decades to understand why. Early attempts assumed that the strength of each force was set by a fundamental constant of nature. But if that were true, all the forces should be roughly comparable at some high-energy scale. Instead, gravity remained far weaker, and nothing about the standard model of particle physics or classical general relativity explained why. When higher dimensional models appeared, the imbalance finally had a possible origin that didn't require rewriting all of physics. The strength of each force could be understood not simply as a number, but as the result of where the force lives. The nuclear forces and electromagnetism live on the brane, so they concentrate their strength in the dimensions you experience. Gravity, however, spreads through the bulk. The on-brane portion is diluted compared to the bulk portion, and the dilution becomes the missing strength you observe. This simple idea could explain why gravity appears weak without requiring any fundamental difference in its true strength. Gravity might be as strong as the other forces in the bulk. It only appears faint on the brane because part of it escapes. To think about the missing strength in a more intuitive way, imagine water flowing from a narrow hose into a wide field. If the water flows into a confined space, the pressure is strong. If the same water spreads across an open field, the pressure becomes gentle. The flow didn't weaken, it dispersed. Gravity might be similar. Its full presence exists in the bulk, but the brain experiences only the portion that curves back into its space. The wider the bulk, the more gravity spreads, and the smaller the fraction that remains focused on the brain. This perspective invites a practical question. How much gravity leaks into the bulk? The answer depends on the structure of the Gravibrane and the shape of the bulk. Different models allow different fractions to escape. Some propose that only a thin layer of gravitational field lines slip into the bulk. Others propose that most of the gravitational field spreads outward. In every version, the missing strength becomes a clue about the size, curvature, or topology of the extra dimensions. Because the weakness is so extreme, the extra dimensions must be large enough for gravity to disperse significantly, but shaped in ways that prevent other forces from entering. Thinking about this subtle behaviour helps clarify why nothing about gravity's weakness is inconsistent with ordinary life. The gravitational field you experience is the portion that returns to the brain. That portion is enough to hold planets together, shape galaxies, and form cosmic structures. But it is also weak enough to allow the formation of stars, the expansion of the universe, and the stability of atoms. If gravity were even slightly stronger, the balance might shift dramatically. Stars might burn too quickly. Planets might collapse into their stars. Galaxies might form differently. The weakness isn't a flaw. It's part of the balance that makes the universe the way it is. Yet the puzzle remains. Why does gravity spread when the other forces do not? The description involving open and closed strings provides one possible answer. In string-based models, the particles carrying the nuclear and electromagnetic forces have endpoints attached to the brain. They cannot move into the bulk. Gravity, carried by closed loops, has no endpoints tying it down. It can move freely. The missing strength might then reflect a fundamental structural difference at the string level. This explanation doesn't require rewriting the known forces. It simply assigns gravity a different kind of carrier, one with the freedom to explore more dimensions. Even if you set string ideas aside, the missing strength still makes sense in models where the brain confines fields. Forces can only act in locations where their fields exist. If a force's field extends through 3 dimensions, it acts strongly there. If the field extends through more dimensions, the effect becomes diluted in any single region. The missing strength disappears as a mystery and becomes a consequence of geometry. While this explanation works well conceptually, physicists still want to quantify it. They want to know the exact amount of gravity that escapes the brain, the size of the dimensions it escapes into, and the behaviour of the Gravibrane that guides the leakage. These details influence predictions for experiments. Even slight deviations from the inverse square law of gravity could reveal the presence of extra dimensions. But so far, the experiments that probe gravity at small distances haven't seen deviations. This doesn't rule out extra dimensions. It only tells researchers that the dimensions must be smaller or shaped differently than those experiments can detect. Another layer of the mystery involves the Planck scale. In traditional physics, the Planck scale is the energy level where quantum effects of gravity become important. It is an enormous number, far beyond what particle accelerators can reach. But if gravity spreads through extra dimensions, then the Planck scale measured on the brain might be misleading. The true Planck scale in the bulk could be much lower. The high number you calculate on the brain might reflect the dilution of gravity, not its true fundamental strength. If the bulk's Planck scale is lower, then gravity unifies more easily with the other forces at high energies. The missing strength becomes a sign that you're only seeing the diluted part of a stronger interaction. This reinterpretation of the Planck scale has important implications for cosmology. In the early universe, energies were much higher. If the bulk's Planck scale was close to those energies, then gravity may have behaved differently. The brain might have been closer to the bulk, the Gravibrane might have been more active, and the leakage between the brain and the bulk might have been more significant. Gravity could have influenced the expansion of the brain in ways that shaped the entire history of the universe. Another clue about the missing strength comes from the behavior of dark matter and dark energy. Although the leading explanations for these phenomena don't rely on extra dimensions, some models suggest that gravity's interaction with the bulk could contribute. If some of the gravitational field is drawn toward structures in the bulk or toward other brains, then the on-brain gravitational behavior might appear distorted. Observers would see discrepancies between visible matter and gravitational effects. This could mimic the influence of missing mass or accelerated expansion. The gravibrane might guide part of the curvature toward or away from the brain, altering what observers measure without requiring new particles. These ideas remain speculative, but they show how geometry can influence what appears to be missing. Even outside cosmology, there are clues hidden in simple observations about gravity. The weakness of gravity in the quantum world, for example, becomes another reflection of its leakage. Quantum particles interact strongly through the nuclear and electromagnetic forces, but gravity's influence at those scales is so faint that it becomes almost irrelevant. Measuring gravity between two quantum particles is impossible with current technology. If gravity were confined to the brain, you might expect a stronger quantum-level influence. But because the gravitational field disperses, almost none of it remains focused enough to influence quantum particles significantly. The missing strength becomes an expected outcome rather than a puzzle. All of these ideas converge on a single theme. The missing strength of gravity is not a sign that gravity itself is fundamentally weaker, but that the world you experience is only part of a larger environment. The brain confines the other forces to a narrow region. Gravity interacts with more. Its weakness is a signal of that greater freedom. The more space gravity has access to, the less it concentrates in the region you inhabit. Thinking through these ideas also highlights why the gravibrane plays such an important role. The gravibrane guides how gravity passes between the brain and the bulk. It influences the fraction of the gravitational field that remains near the brain. It affects how gravitational waves disperse. It shapes the horizon of black holes. It influences how gravity behaves in the early universe. It mediates the missing strength in a way that connects familiar physics to hidden dimensions. As you settle into this understanding, it becomes natural to wonder how a universe filled with extra dimensions would feel if you could perceive them directly. The missing strength suggests that gravity is more active beyond the brain than within it. But because you cannot interact with the bulk in ordinary ways, the deeper structure remains hidden. Yet its influence reveals itself indirectly through the faintness of gravity, the patterns of gravitational waves, and the behavior of black holes. These clues point toward a layered reality, one where the everyday world sits above deeper structures that shape the forces you experience without revealing themselves openly. This naturally leads toward imagining what a universe with multiple dimensions would actually be like from the inside. What motions, shapes, and behaviors would arise if matter, space, and gravity extended beyond familiar directions? And how would the presence of extra dimensions subtly influence the world you experience without ever becoming directly visible? Imagining a universe with more dimensions than the ones you move through each day invites a kind of quiet curiosity. You can picture length, width, and height, because your senses are shaped by the brain. You can imagine motion forward and backward, up and down, left and right. When you think about three-dimensional shapes, objects, and spaces, everything feels familiar because the world has trained your perception to treat these directions as the full extent of physical reality. Yet the mathematics of gravity, the faint pull that shapes the motion of planets and the structure of galaxies, keeps pointing toward the possibility that this familiar space is only part of a larger environment. Higher dimensions don't appear in everyday experience, but their influence might be woven into the behavior of gravity in ways subtle enough that you feel their effects without ever sensing the dimensions themselves. If you were able to experience extra dimensions directly, your perception of space would be different. Not in the sense that you would float or dissolve, but in the sense that motion would feel like it had more options. In 3 dimensions, every direction you can move is a combination of 3 axes. You can walk forward, drift sideways, or climb upward, but every possible motion is built from combinations of those 3. A multi-dimensional universe would provide additional directions, ones that don't fit into the existing framework. The difference wouldn't necessarily feel like floating or expansion. It would feel like discovering that the space around you allows more room for motion than you previously realized, even if that motion isn't accessible through ordinary forces. The reason your senses can't detect those directions comes back to the confinement of forces. Electromagnetism creates sight, touch, chemistry, biology, and the structure of bodies. Those processes occur on the brain because the electromagnetic field is tied to it. Your perception forms from the interaction between matter and light, both of which remain stuck in the 3 dimensions the brain provides. If the brain sits within a larger space, you would never know simply by observing electromagnetic phenomena. Light cannot leave the brain. Your senses cannot follow gravity into the bulk. Everything you interact with is tied to the portion of the universe shaped by the brain itself. Even if the bulk is vast, your experience remains local. But if you could somehow detach perception from the brain, the extra dimensions wouldn't necessarily appear as a spacious void. They would appear as directions, just as ordinary directions appear now. The idea of an extra dimension can seem abstract because you have no instinct for turning or moving into it. But from gravity's perspective, it is simply another axis into which curvature can extend. If your senses were built to detect gravitational curvature directly, instead of relying on electromagnetic signals, the extra dimensions might be visible in subtle shifts. You might sense distortions that don't align with the familiar coordinate system. The geometry of space would feel asymmetric in ways that ordinary perception cannot capture. In higher dimensional models, nothing says the extra dimensions must be large. They could be small, wrapped in loops too tiny to enter physically. If so, gravity would feel their presence through how curvature wraps into those folded directions. The extra dimensions might be curled tightly, like tiny tunnels or circular paths. Gravity could move through them, but matter would not. If you could perceive those directions, they would appear like hidden pathways that exist at every point in space, leading into loops that reconnect with themselves. The universe would feel textured in ways that aren't visible to electromagnetic senses. Every location in space would hold access to those directions, but the paths would be microscopic, shaping gravitational behavior without ever offering room for matter to enter. If the dimensions are larger, the sense of space could change more dramatically. In some models, the extra dimensions are extended, not curled. If you could move through them, you might find yourself entering regions where matter from the brain fades, replaced by shapes of curvature and gravitational fields that shift according to the structure of the bulk. Mass and energy might localize differently. The motion of particles could follow paths that seem impossible when projected onto the brain. A multi-dimensional universe wouldn't resemble a cosmic maze. It would resemble a deeper version of space where the familiar 3-dimensional structures are just surfaces suspended within a broader geometry. Even without direct perception, the influence of extra dimensions would shape how objects behave. If you could feel the higher dimensional structure indirectly, objects might appear to move in ways that don't perfectly match expectations from 3-dimensional physics. The gravitational pull between masses might vary slightly as curvature interacts with the Gravibrane. On cosmic scales, structures might form patterns that reflect not just the distribution of matter on the brain, but also the shape of the bulk. Although current observations remain consistent with 3-dimensional models, the subtle variations that might reveal extra dimensions are still too small to measure. But in a universe with more sensitive instruments or different physical constraints, the higher dimensional structure might become more obvious. Thinking about what the universe would feel like if you could move into extra dimensions also invites a reflection on how matter behaves. Matter, Confined to the brain cannot enter the bulk because the forces that build it cannot extend into extra dimensions. If you were made of matter that could move through the bulk, the brain wouldn't contain you. You would feel gravity differently because gravity would no longer be the only pathway into extra dimensions. Your interaction with the environment would include forces that respond to the full dimensional structure. The notion of motion would expand. You might discover that what feels like stillness in 3 dimensions is actually motion through extra dimensions, or that moving in those dimensions creates effects that appear mysterious to observers confined to the brain. Such ideas illustrate how a multi-dimensional universe doesn't require dramatic visual changes to be profoundly different. Even if the extra dimensions remain invisible, their presence affects everything from gravitational fields to cosmic evolution. Ordinary objects move according to the brain's geometry, but gravity responds to the full environment. The separation between brain-bound forces and bulk-interacting gravity creates patterns and behaviors that reflect the deeper structure without revealing it directly. If you could sense those patterns more clearly, the world would feel layered, with each layer influencing the one above it. The brain itself might also have a feel if you could perceive its structure. The thickness of the brain could matter. If the brain has small depth, particles move in a confined region. If it has larger depth, particles might have specific patterns of motion within that thickness. The Gravibrane, with its softer structure, would add another layer of interaction. If you could sense those structures directly, the universe would feel less like an empty void, and more like an environment shaped by overlapping fields and layers, each contributing to the shape of space. The bulk adds another dimension to this experience. The bulk is not empty. It can contain curvature, fields, or even other brains. If you could sense the bulk, you might experience regions where gravity concentrates or thins out. Motion through the bulk might lead to areas where the brain's influence weakens, replaced by fields that exist only in the higher dimensional space. Transitioning between brain and bulk motion would not resemble stepping through a doorway. It would resemble shifting how you interact with the environment, like switching between mediums where different rules apply. Even though your senses cannot move into those directions, gravity moves through them constantly. When you drop an object, you feel the pull of a gravitational field that includes contributions from curvature in the bulk. When gravitational waves travel through space, they carry information about the full shape of the environment. Those waves encode the structure of the bulk in the way they disperse, stretch, and fade. If your senses were built to detect gravitational waves as easily as electromagnetic light, the world would reveal hidden directional patterns. You might sense a faint component of the wave that doesn't align with any familiar axis, hinting at the presence of extra directions that the brain's geometry cannot explain. A multi-dimensional universe also affects time. Time doesn't require extra dimensions to exist, but the way curvature interacts with extra dimensions could affect how time flows. Near strong gravitational fields, time slows. If curvature extends into extra dimensions, the slowdown might depend partly on the bulk's shape. If you could move into extra dimensions, you might experience time differently. The familiar flow wouldn't vanish, but the relationship between motion and time would include influences from directions you cannot enter now. This doesn't imply time travel or paradoxes, it simply means that the connection between space and time could be richer than what the brain reveals. Cosmic structures also behave differently in multidimensional environments. Galaxies, clusters, and large-scale formations might feel gravitational influences from curvature that extends into the bulk. If some regions of the bulk have different properties, these differences might influence how galaxies cluster. Observers on the brain might see slight variations in gravitational behavior across cosmic scales, reflecting structures beyond the brain. These variations would be subtle, but in a universe where instruments are sensitive to the faintest gravitational patterns, the multidimensional structure could become more visible. Even the concept of distance changes in higher dimensional models. In three-dimensional space, the shortest distance between 2 points is a straight line. But if the brain is curved, or if the bulk allows shortcuts, the true shortest path might pass partially through extra dimensions. Observers on the brain would see no evidence of this because matter cannot enter the bulk, but gravity could take such shortcuts. The gravitational field between 2 points might follow paths that reduce its on-brain component. That behavior could contribute to the missing strength by allowing gravity to disperse more efficiently. Thinking about these possibilities can make the universe feel deeper, more layered, and more structured than the familiar three-dimensional picture suggests. None of this requires imagining fantastical shapes or unreachable realms. It only requires considering that the space you experience is one part of a larger environment. The forces that shape perception are confined to a narrow region. Gravity moves freely through more. The universe feels three-dimensional, not because it lacks higher dimensions, but because the senses built from electromagnetic interactions cannot follow gravity into the deeper structure. Has gravity's faint pull become something you followed across brains through the bulk and into the deepest folds of curved space, it becomes natural to look back at the force itself with a quieter kind of attention. You began with a question about weakness, about why gravity behaves so differently from the other forces that shape matter and energy. But along the way, the faintness stopped looking like a flaw and began to resemble a clue. It pointed toward the brain you inhabit, the higher dimensional bulk surrounding it, the Gravibrane that mediates between them, and the idea that what feels gentle here might be stronger elsewhere. And as these ideas weave together, they form a view of the universe that is more layered, more deliberate, and more interconnected than the familiar picture suggests. Gravity becomes a presence that not only holds planets in orbit, but also hints at structures that remain invisible to every sense except the one governed by curvature. If you were to step back and watch gravity's influence across different scales, the pattern would look surprisingly consistent. Every time you move from one scale to another, gravity reveals a different aspect of the same underlying idea. On the smallest scales, it becomes nearly impossible to detect. Quantum particles move as if gravity barely exists, because the gravitational field that reaches them is the brain-bound fragment of a curvature that is mostly dispersed elsewhere. On the scale of planets, gravity becomes noticeable, guiding orbits and tides, but still requiring enormous masses to create effects strong enough to sense directly. On the scale of stars and galaxies, gravity becomes the architect of structure, gathering matter into spirals, collisions, and clusters that shape the cosmic web. And on the largest scales of all, gravity interacts with the expansion of the universe, influencing how structures form and how the cosmos evolves over billions of years. Across all these scales, gravity remains coherent even as its influence changes. Its behavior mirrors the idea that it extends beyond the brain, returning only a portion of itself to the space you experience. It is not inconsistent, it is layered. If gravity were a voice, it would speak softly in the brain because most of its words drift outward into the bulk. The quietness is not silence, it is dispersion. And dispersion naturally leads to a force that feels gentle unless enormous masses concentrate it. The same perspective helps make sense of why the other forces seem louder. The nuclear forces remain bound to the smallest scales, operating within the depth of the brain and responding to distances far smaller than anything you can see. Electromagnetism shapes chemistry, biology, and the structure of matter, reaching across atoms but remaining confined to the brain's dimensions. These forces focus their influence because they cannot escape. They are bound not by choice, but by structure. Their carriers are tied to the brain, unable to explore the bulk. Gravity isn't tied in the same way. Its carrier has no endpoints that anchor it. The curvature it creates extends into whichever dimension space allows. The brain receives only the part that returns. As ideas like the Gravibrane and the bulk become familiar, they begin to reshape how you interpret even simple observations. When you look at an object fall, you're watching a tiny fraction of a deeper gravitational interaction. The object's path is shaped by the curvature that remains in the brain. The rest of the curvature, the part that spreads through the bulk, doesn't influence the object directly, but it shapes how the field behaves. Even a falling object reflects the larger structure, not because it moves into other dimensions, but because gravity follows the shape of space that includes them. This kind of thinking can make the familiar seem subtly different. When you picture the Earth orbiting the Sun, you might imagine a gravitational pull between two large masses. But from a higher dimensional perspective, the orbit reflects how curvature on the brain and curvature in the bulk balance each other. The Earth's motion follows the line of least curvature in the brain because the bulk absorbs much of the gravitational field that would otherwise change the orbit. The system remains stable not because the brain is isolated, but because it is embedded in a larger structure where gravity interacts with more dimensions than the motion of matter does. One of the interesting consequences of this perspective is how it changes the sense of isolation between systems. In three-dimensional physics, each gravitational interaction comes from the mass you can see. But in a higher dimensional environment, the gravitational field on the brain may include small contributions from curvature shaped by the bulk itself. This doesn't mean you interact with hidden realms directly. It means gravity, acting as a link between layers, responds to structures beyond the brain in ways too faint to detect with current instruments. The faintness itself becomes a reminder that your perspective is shaped by the brain's limitations. This also creates a deeper appreciation for why the universe can expand the way it does. In three-dimensional space, gravity slows expansion by pulling mass together. In higher dimensional models, the expansion depends partly on how the brain moves within the bulk. The Gravibrane might influence how curvature spreads. The bulk might contain fields that interact with the brain's geometry. The presence or shape of extra dimensions could affect how rapidly expansion changes. Even though you don't see these dimensions directly, their influence may be woven into the universe's evolution. The faintness of gravity could reflect how much curvature escapes into the bulk during cosmic expansion. Thinking through these ideas also makes the idea of cosmic balance more interesting. If gravity was stronger on the brain, the universe might not look the way it does. Galaxies might collapse more tightly, stars might merge more frequently, planetary systems might become unstable. The weakness becomes part of the design that allows complex structures to form and remain stable over billions of years. That weakness, shaped by extra dimensions, might be one of the reasons planets can maintain orbits long enough for life to emerge. The same faintness that frustrates experiments in quantum gravity might also contribute to the stability that makes the universe recognizable. These connections suggest that the weakness of gravity, the presence of brains, the behavior of black holes, and the possibility of extra dimensions are not separate ideas. They form a single intertwined story about how the universe organizes itself. Each idea reinforces the others. The weakness of gravity points toward the existence of extra dimensions. The presence of extra dimensions explains the Gravibrane. The behavior of black holes reveals how curvature interacts with hidden directions. The dispersal of gravitational waves hints at the bulk's shape. And the structure of the universe suggests that gravity's faintness plays a role in allowing complexity to emerge. The pieces fit together in a way that feels less like speculation, and more like a gradual uncovering of how reality might be layered. Even though none of this requires dramatic departures from the laws of physics, it invites a broader view of what space might be. You don't need to imagine portals or strange phenomena. All you need to imagine is that the familiar world sits within a larger environment you don't directly perceive. The brain confines most of what you interact with. Gravity interacts with more. The universe feels three-dimensional because your senses depend on forces that can't leave the brain. Gravity feels weak because it doesn't obey that restriction. Letting these ideas settle into a coherent picture makes the universe feel both larger and more structured than it appears. The bulk is not just extra space, it's the environment where much of gravity's behavior plays out. The Gravibrane is not a mysterious boundary, It is the region where brain-bound curvature meets bulk-bound curvature. The missing strength is not an error. It is the natural outcome of gravity interacting with more dimensions than the other forces. If you look at the universe with this understanding in mind, the faintness of gravity becomes one of its most elegant features. It allows stars to live long enough to build heavy elements. It allows galaxies to maintain structure while still expanding with the universe. It allows the brain to hold matter together without collapsing under its own weight. And it allows the bulk to influence the brain without overwhelming it. The balance isn't an accident. It reflects how the universe organizes mass, energy, and space into a layered structure that remains stable across immense spans of time. Watching these ideas unfold gradually creates a deeper appreciation for how gravity weaves through everything. Whether you think about a dropped object, an orbiting planet, a distant black hole, or the expansion of the cosmos, the same faint pull threads through all scales. It connects the brain to the bulk. It shapes the Gravibrane. It responds to curvature in every direction space allows. You never feel the full force because most of it has slipped into directions hidden from view, but the portion that remains is enough to hold the brain's world together. Once you reach this point, thinking about gravity feels less like studying a force and more like following a thread that leads through every layer of the universe. You can trace it through the brain, follow it into the Gravibrane, imagine how it travels through the bulk, and recognize that the faintness you feel is part of a much larger presence. Each idea builds gently on the last without closing the door on new questions. There's always more structure hidden beneath the familiar world, always more to understand about how gravity moves through layers you cannot see, and always more to uncover about how all those layers shape the space where you live.